Hello there, and welcome to Science for Sleep, where curiosity gets cozy, questions move at a gentle pace, and the universe feels a little less overwhelming as the day begins to fade into night. Wherever you happen to be listening from, whether you're curled up under a blanket, leaning back in a chair, or letting the glow of a screen be the last light in the room, I am glad you are here for this quiet journey. Tonight, we are going to drift toward one of the most dramatic and misunderstood objects in the cosmos, something that sounds like it belongs in a science fiction story, but very much belongs in the real universe, the black hole. Before we wander too far into deep space, let me ask you something simple and personal. Where are you listening from right now? Is it late evening, early morning, or somewhere in between? Maybe there is rain tapping softly on a window, or the low hum of a city outside, or just the steady quiet of a room settling into sleep. If this gentle exploration of science feels soothing, or gives you a small pocket of calm in your day, a like or a subscription helps this little corner of curiosity reach others who might be looking for the same kind of peaceful pause. No rush, no pressure, just a small nod to the idea that slow thinking still has a place in a very fast world. Now, let us begin easing into our topic, not with a dramatic plunge, but with a careful step forward. The words black hole tend to carry a lot of emotional weight. They sound dangerous, final, and absolute, like a cosmic trapdoor waiting to swallow anything that strays too close. Movies show them as glowing whirlpools in space, tearing apart ships and stretching astronauts into glowing strands. Headlines often describe them as bottomless pits, places where the laws of physics collapse into a single terrifying point called a singularity. That image is powerful, but tonight we're going to sit with a slightly different idea. The black hole itself is very real, measurable, and surprisingly well behaved in many ways. The singularity, on the other hand, might be something else entirely. To understand what that means, it helps to start with something familiar and gentle rather than something extreme. Think about gravity as you feel it in everyday life. It is the reason your feet stay on the floor, your cup stays on the table, and the air stays wrapped around the planet instead of drifting off into space. Gravity, at its most basic level, is a kind of attraction, a way that mass tells other mass how to move. The Earth pulls on you, and you pull back on the Earth, even if the Earth barely notices. This quiet, constant interaction is happening all the time, and most of the time it feels completely ordinary. Now imagine slowly turning up the strength of that pull. Picture a planet much more massive than Earth, something with several times the mass packed into a similar or even smaller space. The surface gravity there would be stronger. Walking would feel heavier. Lifting your arm would take more effort. If you keep increasing the mass and squeezing it into a tighter and tighter volume, the pull of gravity grows more intense. Stars do this naturally over their lifetimes. They shine for millions or billions of years by balancing two opposing forces. On one side, gravity is trying to make the star collapse inward. On the other, energy from nuclear reactions in the core pushes outward, holding everything up. Eventually, for some stars, that balance ends. When the fuel runs low, the outward push weakens and gravity starts to win. The star begins to collapse under its own weight. For smaller stars, this collapse settles into a dense but stable object like a white dwarf or a neutron star. These are already incredibly strange. A neutron star can pack more mass than the Sun into a sphere about the size of a city. The gravity on its surface is so strong that a teaspoon of its material would weigh billions of tons on Earth. But for the most massive stars, even this is not enough. The collapse continues past the point where neutrons can hold each other up. The core shrinks and shrinks, and the gravitational pull becomes so intense that not even light can escape. That is the moment when a black hole is born. Here is where things often get dramatic, but let us slow down. The black hole, in its simplest description, is not a hole in space in the sense of a tunnel or a tear. It is an object, a region where a certain amount of mass is concentrated so tightly that the escape speed, the speed you would need to leave, is greater than the speed of light. Since nothing can travel faster than light, nothing that crosses a certain boundary can come back out. That boundary is called the event horizon. It is not a physical surface. There is no solid wall, no glowing edge you would bump into. It is more like a point of no return, a quiet line in space that only becomes meaningful once you cross it. From the outside, a black hole behaves in many ways like any other massive object. It has a mass. It can orbit other objects. Other objects can orbit it. If our sun were magically replaced by a black hole of the same mass, the planets would continue to move in their orbits almost exactly as they do now. The Earth would not suddenly spiral inward and vanish. The big difference would be the loss of sunlight, which would make for a very cold and dark situation, but gravitationally things would stay remarkably familiar. This is one of the first clues that black holes are not cosmic vacuum cleaners roaming the universe, swallowing everything in sight. They are part of the cosmic landscape, following the same basic rules as stars and planets, just in a more extreme form. Astronomers have found them by watching how stars move around invisible centers of gravity, by detecting X-rays from hot gas spiraling inward, and even by listening to the faint ripples in space-time created when two black holes collide and merge. These observations tell us very clearly that black holes exist. They are not just mathematical ideas, they are physical objects out there in the universe, doing their quiet, heavy work. Now let us turn our attention to the other word that often travels alongside black holes, the singularity. In popular explanations, the singularity is described as a point at the center of the black hole, where all the mass is crushed into an infinitely small, infinitely dense spot. Infinity is a big, dramatic word, and it tends to stop conversations in their tracks. When people hear that something becomes infinite, it sounds like the ultimate end of understanding, a place where all the rules break and nothing meaningful can be said. But in physics, the appearance of infinity usually raises a different kind of reaction. It often signals not that the universe has done something truly infinite, but that our current theories have reached the edge of what they can describe. To see why, it helps to think about how scientific theories work. A theory is a model, a structured way of describing how things behave based on certain assumptions and mathematical tools. When you push a theory into a situation it was not designed to handle, it can start to give strange answers. Sometimes those answers include infinities. Take a simple example from everyday life. Imagine you have a map of a city that is drawn to show major roads, parks and buildings. It works very well for planning a drive or a walk. Now imagine using that same map to try to find the exact location of a single grain of sand on the sidewalk. The map does not have the level of detail needed for that task. If you try to force it, you might end up with nonsense results. The problem would not be that the sidewalk or the grain of sand is impossible. The problem would be that the map is being used outside its range of usefulness. Something similar happens with our theories of gravity. The main theory we use to describe black holes is Albert Einstein's general relativity. This theory treats gravity not as a force in the traditional sense, but as the curvature of space-time caused by mass and energy. Objects move along paths shaped by this curvature, like marbles rolling across a stretched rubber sheet. This picture has been incredibly successful. It predicts the motion of planets, the bending of light near massive objects, the expansion of the universe, and the behavior of black holes with remarkable accuracy. However, general relativity is a classical theory. It does not include the effects of quantum mechanics, the set of rules that governs the behavior of matter and energy at very small scales. When you use general relativity to describe the very center of a black hole, the equations say that the curvature of space-time becomes infinite at a single point. Density goes to infinity. Tidal forces go to infinity. Time and space, in the math, stop behaving in any familiar way. That point is what we call the singularity. But notice what is happening here. We're using a theory that works beautifully at large scales and pushing it into a regime where very small scales and very high energies matter. That is exactly where quantum effects are expected to become important. The infinity is not necessarily telling us that the universe truly contains an infinitely dense point. It may be telling us that general relativity on its own is not the right tool for describing what happens there. This idea is not unique to black holes. In other areas of physics, infinities have appeared before and later disappeared when better theories were developed. In the early days of studying atoms, some calculations suggested that electrons should radiate away their energy and spiral into the nucleus, leading to a kind of collapse. The math pointed to a problem. The resolution came with the development of quantum mechanics, which provided a new framework that avoided those infinities and described stable atoms instead. So when physicists look at the singularity inside a black hole, many of them see it not as a physical object, but as a signpost. It is pointing to the place where our current understanding runs out. It marks the boundary between what we can confidently describe and what we still need to learn. From the outside, we cannot see inside a black hole. The event horizon blocks any direct information from escaping. That means, in practice, we cannot observe the singularity or whatever replaces it. All we can do is study how black holes behave from the outside and use our theories to make educated guesses about what might be happening within. This makes black holes a kind of natural laboratory for testing ideas about the deeper structure of reality. Some modern approaches to this problem come from attempts to combine general relativity with quantum mechanics into a single, unified framework often called quantum gravity. There are several candidate theories, and they do not all agree with each other, but many of them share an interesting feature. When they are applied to the interior of a black hole, the sharp, infinite singularity tends to soften. Instead of a single point of infinite density, the math suggests a region of extremely high but finite density, or a different kind of structure altogether. One idea is that the core of a black hole might be something like a quantum bounce, where the collapse is halted and redirected by quantum effects. Another suggests that information about everything that falls in is somehow encoded on the surface of the event horizon, in a way that makes the interior less mysterious than it seems. There are also models where space-time itself becomes granular at very small scales, preventing true infinities from forming. None of these ideas has been confirmed yet. They are active areas of research, and each one comes with its own questions and challenges. What they share, though, is a reluctance to accept the singularity as a literal physical point of infinite density. Instead, they treat it as a placeholder, a name we give to a region where our current descriptions fail. This brings us back to the central idea we're gently circling tonight. The black hole is real. We can detect it, measure it, and describe many of its properties with great confidence. The singularity, in contrast, may not be a real, physical thing in the same sense. It may be a feature of our equations rather than a feature of the universe. As you let that idea settle, notice how different it feels from the dramatic images often associated with black holes. Instead of a cosmic monster with an infinitely dense heart, you can think of a black hole as a very heavy, very compact object wrapped in a boundary that hides a region we do not yet fully understand. It is not a hole in reality. It is a place where reality is doing something subtle and complicated, something that invites curiosity rather than fear. In a way, this makes black holes feel more human. They mark the edge of our knowledge. They show us how far our theories can take us and where they start to whisper instead of speak clearly. They remind us that science is not a finished story, but an ongoing conversation between our ideas and the universe itself. You can let the image of a black hole rest in your mind as something solid and real, an object with weight and presence in the cosmos, rather than a bottomless void. And you can let the singularity rest as a question mark, a reminder that even in a universe filled with precise measurements and detailed theories, there are still places where our maps fade into open space. There is something quietly reassuring about the idea of falling, even when the thing you're falling toward is wrapped in mystery. Not the sudden, stomach-lurching kind of fall, that comes from missing a step on the stairs, but the slow, imagined descent that happens in the mind when you picture drifting through space, guided not by engines or maps but by gravity itself. Tonight, that is the kind of fall we're going to explore. Not as an emergency, not as a disaster, but as a gentle way of thinking about what it means to move toward the unknown, especially when that unknown is shaped like a black hole. To begin, it helps to step away from the dramatic images that often come to mind. Forget for a moment the glowing spirals, the stretching astronauts, and the roaring cosmic winds. Instead, imagine yourself very far away from any black hole at all. You're in deep space, where there is no air, no up or down, and no real sense of motion unless something changes around you. In that environment, drifting feels less like falling and more like floating in a vast, quiet ocean. If you're not firing a rocket or pushing off another object, you are weightless, carried along by whatever path you were already on. Now, place a black hole somewhere in the distance. From far away, its gravitational pull is not special. It behaves like the gravity of any other object with the same mass. If you replace the black hole with a star of equal mass, the way you move through space would be nearly identical. You would feel a gentle tug, a gradual bending of your path. There would be no sudden snap, no invisible hand yanking you forward. Gravity, at these distances, is patient. It works over time, shaping trajectories slowly and predictably. This is the first layer of comfort in the unknown. The laws that guide your motion near a black hole are the same ones that guide the motion of planets around stars and moons around planets. There is no hidden rule that suddenly appears when the object in question is dark and compact. The universe does not change its tone just because the scenery gets more extreme. The same equations, the same principles, the same quiet consistency apply. As you drift closer, something interesting begins to happen, but it still does not feel dramatic. The black hole grows larger in your field of view, not as a swirling vortex, but as a region where light behaves differently. If there is glowing gas or dust around it, you might see a bright flattened ring, an accretion disk, where material spirals in, heating up and shining before it crosses the boundary of no return. That boundary, the event horizon, is still just a concept at this distance. It is not a wall you can see or touch. It is a mathematical line in space, defined by the point where the escape speed equals the speed of light. Here is where the idea of falling starts to take on a more specific meaning. In everyday life, falling usually involves an acceleration. You start at rest, and gravity pulls you faster and faster toward the ground. In space, near a black hole, falling can feel very different. If you're far enough from the center and the black hole is large enough, the gravitational field can be surprisingly gentle over the size of your body. You would not feel a strong stretching or squeezing right away. In fact, for a very massive black hole, you could cross the event horizon without noticing anything special at the moment it happens. That thought alone can feel strangely calming. The boundary that defines the black hole, the line that separates what can come back from what cannot, does not announce itself with a flash or a shock. It does not ring a bell or change the lighting. From your perspective, the laws of physics in your immediate surroundings continue to behave normally. Your heart still beats, your clock still ticks, your thoughts still flow. This is not to say that everything is safe or gentle forever. As you continue inward, the differences in gravity between your head and your feet, what physicists call tidal forces, will eventually become extreme. But the key point here is the gradualness of it, especially for large black holes. The universe does not rush this process. It unfolds according to the same steady rules that govern everything else. There is a deeper kind of comfort in that consistency. It suggests that even at the edge of what we understand, even in the presence of objects that challenge our theories and our imagination, the universe remains coherent. It does not suddenly become chaotic or arbitrary. The unknown is not a void where rules disappear. It is a region where the rules we know are still at work, just in combinations and intensities we are still learning to describe. As you picture this slow descent, it can be helpful to think about how motion and gravity are described in modern physics. In general relativity, you're not being pulled by a force in the traditional sense. Instead, you're following the natural path through a curved space-time. The black hole, by concentrating a great deal of mass into a small region, creates a deep curvature like a heavy weight on a stretched fabric. Your path bends not because something is tugging on you directly, but because the space and time you move through are shaped in a particular way. This perspective turns falling into something almost peaceful. You're not being dragged toward a destination. You're simply moving along the path that the universe's geometry lays out for you. The idea that there is a kind of built-in guidance to motion, even in the most extreme environments, can make the unknown feel less like a threat and more like a continuation of a pattern that has always been there. Now shift the focus slightly from the imagined experience of falling to the way we, as observers, think about black holes from the outside. Most of what we know about them comes from watching how other things behave nearby. We see stars orbiting invisible centers. We detect light from gas as it heats up and spirals inward. We measure ripples in space-time from distant collisions. In all of these cases, the black hole itself is not directly visible. It is inferred from its effects. There is something familiar about this. Much of our understanding of the world comes from indirect evidence. We do not see the wind, but we see leaves move. We do not see gravity, but we see objects fall. We do not see time, but we see clocks change and faces age. The black hole fits into this pattern. It is another example of how we build knowledge by paying attention to relationships and consequences rather than to some central hidden thing. This way of knowing can feel comforting because it does not demand complete access. It accepts that some parts of reality are not directly available to us, at least not yet. Instead of insisting on total visibility, it invites patience and careful observation. It encourages a kind of humility, a recognition that understanding can grow without needing to conquer every last mystery all at once. When people talk about the singularity, the supposed infinitely dense point at the center of a black hole, they often imagine it as the ultimate unknown, a place where everything ends. But if you hold on to the idea of falling as a process guided by consistent rules, that image starts to soften. The singularity becomes less like a physical destination and more like a marker in our current maps, a spot where the lines fade because we have not yet drawn them in with enough detail. From this angle, the unknown is not a wall. It is a horizon, much like the event horizon itself. A boundary that tells us not that nothing exists beyond, but that our present tools cannot yet reach any further. There is a quiet encouragement in that. It suggests that future understanding is possible, even if it is not available right now. As you continue to imagine this gentle inward motion, consider how time behaves near a black hole, at least from the perspective of someone watching from far away. To an external observer, your fall appears to slow down as you approach the event horizon. Your signals, carried by light, take longer and longer to reach them. Your clock seems to tick more and more slowly. You never quite appear to cross the boundary. Instead, you fade, becoming dimmer and redder until you are effectively frozen at the edge. This image too can feel oddly soothing. It frames the black hole not as a sudden ending, but as a place where motion stretches out, where change becomes gradual to the point of stillness. Of course, from your own perspective, time continues normally, and you do cross the event horizon. But the fact that different observers can have such different experiences of the same event highlights something gentle and profound about the universe. Reality is not always a single, shared story. It can be layered, with different viewpoints revealing different aspects of the same process. There is a parallel here with how we experience uncertainty in everyday life. From the outside, someone else's journey into the unknown might look slow, tentative, or even paused. From the inside, it can feel active, continuous, and very real. The black hole, in this sense, becomes a kind of cosmic metaphor for how perspective shapes experience. Now let the focus drift back to the idea of comfort. Why should something as extreme as a black hole, something associated with destruction and finality, offer any sense of reassurance at all? Part of the answer lies in the way it fits into the broader story of the universe. Black holes are not anomalies that break the pattern of cosmic evolution. They are part of it. They form from stars. They grow by interacting with their surroundings. They can even influence the formation of galaxies by regulating how gas and dust move on very large scales. In that role, they are not just endpoints. They are participants. They shape what comes next, even if the details of how they do so are still being studied. This idea can make the unknown feel less isolated. It places it within a network of relationships, causes, and effects that stretch across billions of years and countless light years of space. There is also something grounding about the fact that black holes obey limits. They are defined by just a few basic properties: mass, spin, and electric charge. This simplicity is sometimes summarized by a phrase that physicists use, saying that black holes have no hair, meaning no extra distinguishing features. While the phrase is playful, the idea behind it is serious. It suggests that, despite all the complexity of what might fall into a black hole, the object itself can be described in a very clean, minimal way. That kind of simplicity at the heart of something so extreme can feel like a form of order. It hints that the universe, even at its most dramatic, leans toward patterns that can be captured in a few clear ideas. The unknown in this sense is not a tangled mess. It is a place where simplicity and complexity meet in ways we are still learning to articulate. As you sit with these thoughts, it is worth noticing how much of this exploration happens in the imagination. None of us can actually fall into a black hole, and even if we could not report back. The journey we are taking is a mental one, guided by equations, observations, and a willingness to picture scenarios that lie far beyond everyday experience. That willingness itself is a kind of comfort. It shows that the human mind is not limited to what is immediately present. It can reach outward, across space and time, and engage with ideas that stretch the boundaries of intuition. The unknown does not have to be a place of fear. It can be a place of curiosity, a space where questions are allowed to exist without immediate answers. This attitude toward the unknown is reflected in how scientists approach black holes and the singularity question. There is no rush to declare the mystery solved. Instead, there is a steady, careful process of building better models, designing more sensitive instruments, and finding new ways to test ideas against observation. Progress comes in small steps, each one adding a little more detail to the picture. You can think of this process as a kind of collective falling, not toward a final point, but toward deeper understanding. Each generation moves a little closer to the boundaries of what can be known, guided by the same underlying rules supported by the work that came before. The unknown, when approached slowly and thoughtfully, does not have to feel like a void. It can feel like an open space, a region where questions are not signs of failure, but invitations to keep looking. It is easy to build an entire picture of black holes without ever opening a physics book. All you need is a handful of movies, a few dramatic documentaries, and perhaps an image of a glowing spiral pulled from a headline. In those stories, black holes roar, twist, and tear apart anything that dares to come near. Spaceships are stretched into thin strands of light. Time freezes. The universe itself seems to bend in protest. These scenes are exciting, memorable, and very good at one thing: making black holes feel like cosmic villains waiting in the dark. Tonight, let us take a calmer look. Not to strip away the wonder, but to replace the dramatic promises with something quieter, steadier, and in many ways more interesting. Because black holes really do exist, and they really are strange, but the way they behave in the universe is far less theatrical and far more subtle than most stories suggest. To start, it helps to remember how we usually meet black holes in fiction. They often appear suddenly, filling the screen with swirling light and thunderous sound, as if space itself were an ocean being drained down a glowing sink. Everything nearby is pulled in at once. Planets break apart, stars vanish. The sense is that a black hole is a kind of roaming disaster, something that cannot help but consume its surroundings wherever it goes. The real universe is much quieter. Black holes do not wander through space like hungry predators. They are born in specific places, usually from the collapse of massive stars, and they tend to stay where they form or move only as part of a larger system, like a galaxy or a pair of orbiting objects. Most of them spend their lives doing very little that would draw attention. They sit in the dark, interacting gravitationally with their surroundings, in much the same way any other massive object would. If you could watch a black hole from a safe distance over millions of years, you would likely be bored. There would be no constant fireworks, no steady stream of stars being torn apart. Most of the time, nothing dramatic happens at all. This leads to one of the first big differences between the cinematic version and the real thing. Black holes are not automatic vacuum cleaners. They do not pull everything nearby into them just because it exists. Gravity, even very strong gravity, still follows the same rules it always does. Objects need to get very close, or be on a path that leads them inward, to actually fall in. Think about the sun for a moment. It has a strong gravitational pull, strong enough to hold the planets in their orbits for billions of years. Yet the Earth does not spiral inward and disappear. It stays in a stable path because its sideways motion balances the sun's pull. The same is true for a black hole of the same mass. If the sun were replaced by a black hole, the Earth's orbit would remain almost exactly the same. There would be no sudden plunge, no dramatic change in motion. The difference would be in the light and heat, not in the gravity. This idea alone reshapes the way black holes feel. Instead of being cosmic traps that reach out across space, they become part of the same gravitational landscape as everything else. Their presence matters, but it matters in a familiar way. Another promise that movies often make is that black holes are always visible, always marked by glowing rings and swirling light. In reality, a black hole by itself is completely dark. It does not emit light. It does not reflect light. If there were no material around it, it would be almost impossible to see directly. What we usually observe is not the black hole, but what is happening near it. Gas and dust that drift too close can form a disk as they spiral inward. Friction and compression heat this material to extremely high temperatures, causing it to glow brightly, often in X-rays. This glowing disk can be spectacular, and it can stretch across huge distances, sometimes larger than our entire solar system. But the black hole itself remains hidden at the centre, a quiet region where light can no longer escape. This distinction is important because it highlights how much of what we associate with black holes actually belongs to their surroundings, not to the object itself. The drama happens in the neighbourhood, not at the core. There is also the matter of sound. Films often portray black holes as roaring, rumbling, or producing deep, ominous noises. In space, sound does not travel the way it does in air. There is no medium for it to move through. A black hole swallowing a star would not produce a boom you could hear. The event would be silent, at least in the usual sense of sound. What it would produce are ripples in space-time, gravitational waves, which we can now detect with very sensitive instruments on Earth. These waves are sometimes translated into sound for us to listen to, but that is a kind of creative interpretation, not an actual noise travelling through space. This brings us to another common promise, the idea that black holes freeze time completely, creating a kind of eternal moment at their edge. The truth is a little more nuanced. From far away, an observer does see objects appear to slow down as they approach the event horizon. Signals take longer to arrive. Light becomes stretched to longer wavelengths. The object seems to fade and linger at the boundary. From the perspective of the object itself, though, time continues normally. A clock carried along would tick just as it always has. The person or probe crossing the event horizon would not feel time stop. This difference in perspective is not a trick or a contradiction. It is a feature of how time and space are woven together in the universe. Different observers, moving differently and experiencing gravity differently, can measure time in different ways. This is one of those cases where the real story is quieter but deeper than the dramatic version. Instead of a single, absolute experience of time, there are many layered experiences, each valid in its own frame of reference. Movies also love the idea that black holes instantly destroy anything that comes near, pulling it apart in a violent display of stretching and tearing. This effect, sometimes called spaghettification, is real, but it depends on the size of the black hole. Near smaller black holes, the tidal forces close to the event horizon can be very strong. The difference in gravity between one part of an object and another can become extreme, leading to stretching along one direction and squeezing along another. Near very large black holes, however, those tidal forces at the event horizon can be surprisingly mild. An object could cross the boundary without being torn apart immediately. The stretching would become severe only deeper inside. This does not make the situation safe in any practical sense, but it does change the character of the experience from an instant, dramatic destruction to a more gradual process. There is something almost understated about that. The most extreme objects in the universe do not always announce themselves with the most extreme effects right away. Another cinematic promise is that black holes are rare, exotic anomalies scattered sparingly through the cosmos. In reality, they're quite common. Our own galaxy likely contains millions of them. Most are stellar mass black holes formed from individual stars. At the centre of the Milky Way, there is a supermassive black hole with a mass millions of times that of the Sun. Similar giants sit at the centres of most large galaxies. These central black holes are not just passive residents. They can influence how galaxies evolve. When they are actively pulling in material, they can release enormous amounts of energy into their surroundings, heating gas and affecting the rate at which new stars form. In this way, black holes become part of the large-scale story of how structures in the universe grow and change over billions of years. This role is rarely shown in popular stories, but it adds another layer of reality to the picture. Black holes are not just endpoints. They are participants in a long, ongoing process. There is also the promise that black holes are completely isolated, cut off from the rest of the universe once something falls in. The truth is more subtle. While information about what crosses the event horizon cannot escape in the usual way, black holes themselves are not entirely disconnected. They can merge with other black holes, combining their masses and spins. They can emit radiation, at least in theory, through a process known as Hawking radiation, which suggests that black holes can very slowly lose mass over extremely long timescales. This idea that even black holes are not perfectly eternal adds a gentle note to their story. Given enough time, far more than the current age of the universe, they may fade away, returning their energy to the cosmos in a different form. The universe, in this view, does not build anything that lasts forever, not even its darkest, heaviest objects. One of the biggest differences between the promised black holes of fiction and the real ones of physics lies in how we know about them. In stories, they are often encountered directly, faced head-on by characters who can see, hear, and react to them in real time. In science, black holes are known mostly through careful measurement and inference. Astronomers track the motion of stars near invisible centres. They analyse the light from hot gas. They detect tiny distortions in space-time from distant mergers. This method of discovery is slow and patient. It involves long periods of observation, careful checking of data, and constant comparison with theoretical models. The result is a picture that is less visually dramatic but more reliable. Each piece of evidence adds to a growing body of knowledge that can be tested, refined, and sometimes corrected. There is a kind of quiet satisfaction in that process. It shows that understanding does not always come from bold confrontations with the unknown, but often from steady attention and a willingness to let patterns emerge over time. Another promise that often appears in stories is that black holes are perfect symbols of ultimate mystery, places where science simply gives up. While it is true that there are deep questions about what happens inside them, it is also true that black holes are among the best tested predictions of general relativity. The way they affect their surroundings, the way they merge, and the way they warp space-time all match the theory's predictions remarkably well. In that sense, black holes are not just mysterious, they're also reassuring. They show that our understanding of gravity, at least on large scales, is on solid ground. The unknown parts, such as the nature of the interior and the fate of information, stand out precisely because so much else works so well. This balance between the known and the unknown is part of what makes black holes so compelling. They are not blank spots on the map. They are regions where the map is detailed and precise up to a certain boundary and then fades into questions. That fading edge invites exploration rather than resignation. There is also a personal dimension to how we relate to these objects. The way they are portrayed in movies often mirrors how we think about uncertainty in our own lives. The black hole becomes a symbol of the final, the overwhelming, the thing that swallows plans and possibilities. The real black hole, with its quiet presence and steady behavior, offers a different metaphor. It suggests that even the most unknown parts of reality are embedded in a larger, consistent framework. The universe does not suddenly change its character when we reach the edge of our understanding. It continues to follow its patterns, even if we have not yet learned how to describe all of them. As you let this more grounded image settle in, notice how it changes the emotional tone of the idea. The black hole becomes less of a threat and more of a feature, less of a monster and more of a landmark. It marks a place where the universe does something extreme, but not arbitrary. This does not take away the sense of wonder. If anything, it deepens it. There is something remarkable about an object that can be described by a few simple properties, influence the structure of entire galaxies, and still hide a region that challenges our best theories. That combination of simplicity and depth is rare and powerful. The stories we tell in movies often need clear conflicts and dramatic stakes. The universe does not. It unfolds according to its own rhythms, with moments of violence and moments of calm, with long stretches of quiet punctuated by brief, intense events. Black holes fit naturally into that rhythm. They are born in stellar explosions, grow through slow accretion and occasional mergers, and spend most of their time simply being what they are. Long before anyone pointed a telescope at the sky or wrote an equation about curved space-time, gravity already had a quiet reputation. It was the reason apples fell, rivers flowed downhill, and your feet stayed planted on the floor instead of drifting off into the air. It was familiar, reliable, and almost invisible in its everyday presence. Yet somewhere in the deep logic of the universe, that same gentle pull learned how to do something that sounds almost impossible at first, to hold on to light itself. That idea alone can feel strange in a comforting way. Light is often treated as the ultimate traveller, the fastest messenger, the one thing nothing can catch. It crosses empty space at a speed so high that, on human scales, it might as well be instant. Sunlight takes a little over 8 minutes to reach Earth, which seems slow only because the distance is unimaginably large. On the scale of a room, light moves so quickly that the delay is too small to notice. So how does gravity, something we associate with slow, steady motion, learn to trap something that fast? To ease into that question, it helps to start with a simpler picture of motion. Imagine throwing a ball straight up into the air. It rises, slows down, stops for a brief moment at the top of its arc, and then falls back down. The reason it comes back is gravity. The Earth's pull slows it, takes away its upward motion, and eventually reverses it. Now imagine throwing the ball faster. It goes higher before turning around. Throw it faster still, and it goes higher again. There is a certain speed, called the escape velocity, where if you throw the ball that fast, it will never come back down. It will keep moving upward, leaving Earth's gravitational influence behind. For Earth, that speed is about 11 kilometers per second. This idea of escape velocity is a helpful stepping stone. It tells us that whether something falls back or keeps going depends on how fast it is moving and how strong the gravitational pull is. Light in everyday situations always moves at the same speed. You cannot throw light faster or slower. It simply travels at its own built-in pace. On Earth, that speed is far greater than the escape velocity, so gravity barely affects it. The path of a beam of light in your room is, for all practical purposes, a straight line. But the universe is not limited to Earth's level of gravity. There are objects far more massive, far more compact, and far more intense in their gravitational pull. Near those objects, the idea of escape velocity takes on a new scale. Imagine an object so massive and so tightly packed that its escape velocity is equal to the speed of light. At that point, even light would not have enough speed to get away. Once it moved inward past a certain boundary, it would be trapped, unable to climb back out. That is the basic idea behind how gravity can trap light. It does not grab it like a hand. It shapes the space and time around it in such a way that all the possible paths light could take lead inward. To see how this works more clearly, it helps to shift from the older, force-based picture of gravity to the one introduced by Albert Einstein. In general relativity, gravity is not a pull acting across space. It is the curvature of space-time itself. Massive objects tell space and time how to bend, and space and time tell objects, including light, how to move. In this view, light always follows the straightest possible path through space-time. The key is that straight does not always mean what it does on a flat surface. On a curved surface, the straightest path can look bent to an outside observer. A simple example is walking on the surface of the Earth. If you start at the equator and walk straight north, you will eventually reach the North Pole. From a map's perspective, your path curves, but from your own perspective, you are always moving straight ahead. The surface itself is curved, and your straight path follows that curvature. Light near a massive object does something similar. The space-time around the object is curved, so the straightest path through that region bends. This is why we see light from distant stars bend as it passes near the sun, an effect known as gravitational lensing. The sun's mass curves space-time just enough to shift the apparent position of the stars behind it. This bending of light is usually gentle and subtle. It takes careful measurements to detect. But as you move closer to more massive and compact objects, the curvature becomes stronger and the bending becomes more dramatic. Near a black hole, the curvature of space-time is so extreme that the straightest possible paths for light can form closed loops or lead inexorably inward. There is a region where light can orbit the black hole, travelling in circles, caught in a delicate balance between moving forward and falling inward. This region is sometimes called the photon sphere. Inside a certain boundary, the event horizon, all the possible straight paths through space-time lead deeper in. There is no path that leads outward. Light does not slow down or run out of energy. It simply follows the geometry it is given, and that geometry points only one way. This geometric way of thinking can feel oddly gentle. Instead of imagining light being yanked or crushed, you can picture it as faithfully following the shape of the space it moves through. The trapping happens not because light changes, but because the stage it moves on becomes so deeply curved that there is no outward direction left. There is a quiet elegance in that. The same rule applies everywhere. Light always takes the straightest path available. The difference near a black hole is that straight leads somewhere very different than it does in empty space. To understand how gravity learned to do this, it is worth stepping back and looking at the broader history of how we came to this idea. For centuries, gravity was described using Isaac Newton's framework. In that picture, gravity was a force acting at a distance. Objects pulled on each other, and light, which was often thought of as a stream of tiny particles, could, in principle, be affected by that pull. In fact, even in the 18th century, scientists speculated about the possibility of dark stars, objects so massive that their escape velocity would exceed the speed of light. This was before the modern understanding of light and long before Einstein. The idea was there in a rough conceptual form, waiting for better tools to make it precise. Einstein's contribution was to provide those tools. By linking gravity to the geometry of space-time, he created a framework where the trapping of light was not just possible, but a natural outcome of the equations. When enough mass is concentrated in a small enough region, the curvature becomes strong enough to form a boundary from which no light can escape. This was not just a theoretical curiosity. The equations predicted a specific relationship between the mass of an object and the size of this boundary. That relationship defines what is now called the Schwarzschild radius, the radius of the event horizon for a non-rotating black hole. For an object like the Earth, that radius is tiny, far smaller than an atom. For the Sun, it is about 3 kilometers. For a supermassive black hole at the center of a galaxy, it can be millions or even billions of kilometers across. These numbers give a sense of how compact a black hole really is. It is not just heavy, it is heavy in a very small space. That combination is what allows gravity to shape space-time so strongly that even light cannot find a way out. There is another layer to this story that adds to its calm, almost methodical feeling. The formation of a black hole, and therefore the formation of a region where light is trapped, is not instantaneous. It happens as a star collapses, as matter falls inward, and as the curvature of space-time deepens. The event horizon forms and grows as the mass crosses the critical radius. From the outside, this process can appear to stretch out in time. Signals from the collapsing star take longer and longer to escape as they climb out of the deepening gravitational well. The light becomes redder and fainter. The star seems to freeze and fade at the boundary. From the inside, the collapse continues. The star's material moves inward, and the region where light cannot escape becomes a permanent feature of the space-time geometry. This dual perspective, one from the outside and one from the inside, is a recurring theme in the story of black holes. It reminds us that what is happening depends on how and where you are watching from. The trapping of light is not a single dramatic moment. It is a gradual change in the structure of space-time. There is also a subtle but important point about what it means for light to be trapped. It does not mean that light piles up inside a black hole like water in a container. Light that crosses the event horizon continues on its path. It does not bounce around or form a glowing core. It simply moves deeper into the curved space-time, following the only directions available to it. This reinforces the idea that the black hole is not a container or a pocket. It is a region defined by how paths through space-time behave. The trapping of light is a statement about geometry, not about walls or barriers. As you let this settle, it can be interesting to think about how different this picture is from the one suggested by everyday language. Words like hole, trap, and edge make it sound as though there is a physical structure doing the work. The reality is more abstract and in a way more peaceful. The work is done by the shape of space-time itself, a shape that emerges naturally from the presence of mass and energy. This also helps explain why the singularity, the supposed infinitely dense center, is not required for the trapping of light. The event horizon, the boundary that light cannot cross outward, is defined entirely by the mass and size of the object. It exists whether or not there is an actual point of infinite density at the center. In other words, gravity does not need an infinitely small, infinitely dense core to learn how to hold on to light. It only needs enough mass in a small enough region to curve space-time deeply. The trapping happens at the horizon, not at the center. This distinction is important for the broader idea we've been exploring, that the black hole is real and well-defined, while the singularity may be a feature of our current theories rather than a physical object. The boundary that traps light is something we can describe, measure, and even observe indirectly. It is a concrete part of the universe's structure. As you imagine light approaching this boundary, picture it not as a desperate struggle, but as a steady journey along a path that gradually turns inward. Far away, the path looks almost straight. Closer in, it curves more. At the horizon, all the paths lead in the same direction. There is no sudden snap, just a quiet alignment of possibilities. This way of thinking can feel surprisingly gentle. It takes something that sounds violent and recasts it as a matter of direction and shape. The universe is not slamming a door on light. It is shaping the space light moves through so that the door is no longer part of the map. There is a broader philosophical note here as well. The idea that light, the ultimate messenger, can be guided and limited by the structure of space-time suggests that even the most fundamental aspects of reality are relational. Nothing exists entirely on its own. How something behaves depends on the context it is in, the environment it moves through, and the structures that surround it. Gravity. Learning to trap light is not a story about a force becoming stronger in isolation. It is a story about how mass, space, and time interact to create new possibilities. It is a story about relationships, not just properties. For now, it is enough to rest with the idea that the trapping of light is not a violent act but a geometric one. Light follows the straightest paths it can. Gravity shapes those paths. When the shape becomes deep enough, the paths lead inward, and the light goes with them, not because it is forced, but because that is simply where the road goes. And in that quiet, consistent behavior, there is a sense of continuity. The same rule that guides a beam of light bending around the sun guides a beam of light approaching a black hole. The difference is one of degree, not of kind. The universe does not change its language when it speaks in extremes. It uses the same grammar, the same basic ideas, just arranged in more intense ways. As we keep following this grammar step by step, we move closer to the places where our understanding becomes thin and our questions become more interesting. There is no need to rush that movement. The story of how gravity learned to shape light is not a single moment, but a long unfolding, one that stretches from simple ideas about falling objects to deep insights about the fabric of reality. There is something almost peaceful about the phrase, point of no return. It sounds dramatic at first, like the moment in a story when a character crosses a line and everything changes forever. But in the context of a black hole, this point is not marked by a flash of light, a sudden jolt, or a warning sign floating in space. It is quiet, invisible, and defined not by what you see or feel in the moment, but by what becomes impossible afterward. This is the event horizon, and it sits at the heart of how black holes shape what can be known about the universe. To begin thinking about it, it helps to strip away the image of a solid edge or a glowing boundary. The event horizon is not a surface in the usual sense. You cannot touch it. You cannot bump into it. There is no physical barrier there at all. Instead, it is a mathematical boundary, a line in space-time that separates two kinds of futures. On one side, paths through space and time can still lead outward. On the other side, every possible path leads deeper in. That idea can feel abstract, so let us anchor it in something more familiar. Imagine standing in a river that flows steadily toward a waterfall. Far upstream, the current is gentle. You can swim against it, move sideways, or drift along. As you move closer to the edge, the current becomes stronger. At some point, the flow becomes so fast that no matter how hard you swim, you cannot make progress back upstream. Cross that point and the waterfall becomes inevitable, even if you do not see it yet. In this picture, the water is like the flow of space-time and you are like a beam of light or a particle moving through it. The event horizon is like the point in the river where the current speed matches your maximum swimming speed. Beyond that, all motion leads in the same direction. The key difference, of course, is that in a black hole, the current is not water. It is the structure of space-time itself. Near a massive, compact object, space and time are curved in such a way that the natural paths, the straightest possible routes through that geometry, tilt inward. Far away, those paths can point in many directions, Closer in, they begin to lean. At the horizon, they all point toward the center. This is why light cannot escape. Light always follows the straightest path available. When all the straightest paths lead inward, light goes inward too. What makes this boundary especially interesting is how unremarkable it can feel from the perspective of someone crossing it, at least for a large black hole. If the black hole is massive enough, the tidal forces at the horizon can be small. You would not feel a sudden stretching or squeezing. There would be no physical sensation that announces, "You are crossing the line now." Your instruments would continue to work. Your clock would continue to tick. The laws of physics in your immediate surroundings would look the same as they did just moments before. The horizon does not create a local disturbance. It changes the global structure of what is possible. This difference between local experience and global consequence is one of the quiet, profound aspects of the event horizon. In your own frame of reference, nothing special happens at the crossing. In the larger picture of space-time, everything about your future changes. From the outside, the story looks very different. An observer far away never sees you cross the horizon. As you approach it, the signals you send take longer and longer to reach them. Your light becomes stretched to longer wavelengths, fading from visible to infrared to radio, and eventually becoming too weak to detect. To that distant observer, you appear to slow down and freeze at the boundary, becoming dimmer and dimmer without ever quite disappearing. This is not an illusion in the usual sense. It is a real effect of how time and gravity interact. Strong gravity slows the passage of time relative to regions with weaker gravity. The closer you get to the black hole, the more pronounced this effect becomes. From far away, it looks as though your clock is ticking more and more slowly. This layered view of the same event highlights something subtle about reality. There is no single, universal story that everyone must agree on. Different observers, in different states of motion and in different gravitational environments, can legitimately describe the same sequence of events in different ways. The event horizon sits at the center of this difference. It is a place where perspectives diverge sharply, even though the underlying physics remains consistent. There is another way to think about the horizon that adds to its quiet character. Instead of imagining it as a fixed shell around the black hole, you can think of it as something that responds to what happens. If more matter falls in, the mass of the black hole increases and the horizon grows. If over extremely long times the black hole loses mass through processes like Hawking radiation, the horizon shrinks. In this sense, the event horizon is not a rigid boundary. It is a dynamic feature of space-time, adjusting to the balance of mass and energy. It is a record of what has been absorbed and what remains. This brings us to one of the most intriguing questions associated with event horizons, the question of information. In everyday life, when something happens, information about it can spread outward. Light carries images, sound carries vibrations, signals carry data. The world leaves traces of itself. At the horizon, that outward flow stops. Information about anything that crosses the boundary cannot reach the outside universe in the usual way. This raises a deep puzzle. According to the rules of quantum mechanics, information is not supposed to be destroyed. It can be transformed, scrambled, or hidden, but it should not vanish completely. So what happens to the information about the things that fall into a black hole? For a long time, this was an open problem that sat at the intersection of gravity, quantum theory, and thermodynamics. Some thought that black holes might truly destroy information, which would require a revision of quantum mechanics. Others suspected that the information was somehow preserved, but in a way that was not obvious. One of the ideas that emerged is that information might be encoded on the event horizon itself, spread across its surface in a very fine quantum-level pattern. In this view, the horizon is not just a boundary of no return. It is also a kind of ledger, recording, in an extremely subtle way, what has passed through it. This idea connects to something called the holographic principle, which suggests that the information contained in a volume of space can be represented on its boundary. The event horizon becomes, in this sense, a two-dimensional surface that holds the story of a three-dimensional region. Whether this picture is exactly correct is still being studied, but it highlights how the event horizon is more than just a line you cross. It is an active participant in the physics of black holes, a place where ideas about space, time, and information come together. There is also a thermodynamic side to the horizon that adds another layer of calm complexity. Black holes have a temperature. They have an entropy, a measure of the number of microscopic states that correspond to their macroscopic appearance. This entropy is proportional to the area of the event horizon, not the volume inside. This is another hint that the horizon plays a special role. It suggests that, in some deep sense, the content of a black hole is tied to its boundary rather than to what lies at the centre. When Stephen Hawking showed that black holes should emit a faint radiation due to quantum effects near the horizon, it reinforced this connection. The radiation is incredibly weak for large black holes, but over unimaginable timescales, it could cause them to lose mass and eventually evaporate. In that slow fading, the horizon would shrink, and whatever information it holds would, in some form, be released back into the universe. The details of how that might work are still debated, but the idea itself turns the horizon into a bridge between what goes in and what might one day come out, rather than a simple, permanent wall. As you let these ideas settle, notice how different this is from the way points of no return are usually portrayed. In stories, crossing such a point often means the end of the narrative, a finality that closes off all possibilities. The event horizon, by contrast, opens up a wide landscape of questions and connections. It is less a conclusion and more a junction where different branches of physics meet. There is also something gentle about the scale at which all of this happens. The horizon of a stellar mass black hole might be only a few kilometers across. The horizon of a supermassive black hole can be larger than the orbit of Mercury, or even larger than the entire solar system. Yet in both cases, the underlying principle is the same. The boundary is defined by a simple relationship between mass and the structure of space-time. This simplicity in the definition contrasts with the richness of the consequences. From that one boundary flow questions about time, information, thermodynamics, and the ultimate fate of matter and energy. It is worth pausing to reflect on how we, as observers, come to know about something we can never directly see. No telescope can image the event horizon as a sharp line. What we see instead are the shadows and distortions it creates in the light around it. In recent years, astronomers have used networks of radio telescopes spread across the Earth to create images of the regions around supermassive black holes. These images show bright rings of light surrounding dark centers, silhouettes shaped by the bending of light near the horizon. They are not photographs in the everyday sense, but they are visual confirmations that these boundaries exist where the theory says they should. There is something quietly satisfying about that. A concept that began as a solution to an equation becomes, over time, something we can map and measure even if indirectly. The event horizon moves from being a purely abstract idea to being a feature of the universe we can point to and say, there, that is where the paths of light change. As this understanding deepens, the horizon also becomes a place where our confidence meets our uncertainty. We can describe its size, its shape, and many of its effects with precision. What happens beyond it remains largely hidden. This balance can feel comforting in its own way. It suggests that the universe does not reveal everything at once. It offers layers of understanding, each one accessible with the right tools and the right questions, and each one hinting at something further on. From a more human perspective, the idea of a quiet point of no return can resonate with how change often works in our own lives. There are moments that do not feel dramatic when they happen, but that, in retrospect, mark a clear shift in direction. A decision made, a path taken, a boundary crossed without fanfare. Only later does the full weight of that crossing become clear. The event horizon embodies this idea on a cosmic scale. It is a transition that does not announce itself locally, but that reshapes the entire future of whatever passes through it. You can let the image of the event horizon rest as a calm, steady boundary, not a dramatic cliff, but a smooth, continuous surface in the geometry of space-time. It is a line drawn not in matter, but in possibility. Light, time, and information approach it and find that the directions they can take narrow and then converge. From one side, the universe remains open. From the other, the future leads only inward. And in that quiet convergence, there is a sense of order rather than chaos. The universe is not slamming a door, it is shaping a path. There is a particular kind of pause that happens in a conversation when someone uses a word that feels heavier than the rest. It does not stop the discussion, but it changes the tone. It invites caution, maybe even a little reflection, before moving on. In the world of physics, the word singularity often carries that kind of weight. It sounds final, absolute, and almost mythical, like a place where explanation gives up and mystery takes over completely. And yet, for many physicists, the word does not inspire awe so much as it inspires unease. To understand why, it helps to step back from black holes for a moment and think about what a singularity actually means in a mathematical sense. In everyday language, we might use the word to mean something unique or special. In mathematics and physics, it has a more specific and less poetic meaning. A singularity is a point where a mathematical description stops working, where certain quantities blow up to infinity or become undefined. Imagine drawing a simple curve on a piece of paper, something smooth and continuous. Now imagine a point on that curve where it suddenly shoots straight up, becoming infinitely steep. At that point, the usual way you describe the slope of the curve no longer works. The slope becomes infinite. That point is a kind of singularity in the math. It is not necessarily telling you that something physically infinite exists on the page. It is telling you that the particular way you are describing the curve cannot handle what is happening there. This distinction is subtle but important. In physics, equations are our maps of reality. They are not reality itself. When those equations produce infinities, it often signals that the map has reached the edge of its usefulness, not that the terrain itself has become truly infinite. With that in mind, return to the black hole. In the framework of general relativity, when you follow the equations inward past the event horizon, they predict that the curvature of space-time becomes infinite at a single point, the center. Density becomes infinite. Tidal forces become infinite. Time and space, as described by the math, stop behaving in any familiar way. That point is what we call the singularity. On paper, it sits there as a stark, dramatic feature. But in the minds of many physicists, it raises a red flag. Infinities in physical theories are often treated as signs of trouble. They suggest that something important has been left out of the description. There is a long history of this in science. At the end of the 19th century, classical physics ran into a problem known as the ultraviolet catastrophe. Calculation suggested that a hot object should emit an infinite amount of energy at short wavelengths. Obviously, that does not happen in the real world. The infinity in the equations was a clue that the theory was missing something. The resolution came with the development of quantum mechanics, which introduced new rules and eliminated the infinity. Another example appears in the early models of the atom. Classical physics predicted that electrons orbiting a nucleus should radiate energy and spiral inward, collapsing the atom. Again, that does not happen. The problem was not that atoms were secretly collapsing. The problem was that the theory being used did not apply at that scale. Quantum mechanics replaced it with a new framework that produced stable atoms without infinities. These stories shape how physicists react when they see an infinity appear in their equations. It is not usually taken as a final answer. It is taken as a hint. So when general relativity predicts a singularity at the center of a black hole, many physicists interpret that not as a literal point of infinite density, but as a sign that general relativity by itself is being pushed beyond the domain where it can be trusted. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. It works incredibly well at describing large-scale structures like planets, stars, galaxies, and the overall expansion of the universe. But it does not include the effects of quantum mechanics, which become important at very small scales. Near the center of a black hole, the densities and energies involved are expected to reach levels where quantum effects cannot be ignored. At that point, using a purely classical theory is like trying to describe the behavior of individual atoms using the rules of fluid flow. You might get some rough ideas, but the details will be wrong, and the math may start to produce nonsense. The singularity, in this view, is the place where the mismatch becomes obvious. There is another layer to the discomfort around the word, and it has to do with predictability. One of the goals of physics is to take a set of initial conditions and use the laws of nature to predict what will happen next. A singularity, by definition, is a place where the laws, as currently written, cannot tell you what happens. The equations stop giving meaningful answers. In some cases, this can create a situation known as a breakdown of determinism. If you cannot calculate what comes out of a singularity, you cannot fully predict the future of the system. For a discipline built on the idea that the universe follows consistent, discoverable rules, this is deeply unsettling. There is a famous example of this in cosmology, the singularity associated with the Big Bang. When you run the equations of general relativity backward in time, they suggest that the universe began in a state of infinite density and temperature. That point, like the one at the center of a black hole, is a singularity. Physicists are similarly uneasy about this. It marks a place where their current theories cannot describe what happened. Many suspect that a more complete theory, one that includes quantum effects, would replace the singularity with something else. Perhaps a very small, very hot, but still finite state. The parallel between black hole singularities and the Big Bang singularity is not lost on researchers. In some models, the two are even connected. A black hole in one universe might correspond to a kind of Big Bang in another. These ideas are speculative, but they highlight how singularities tend to appear at the edges of our understanding, both in the very small and the very large. Another reason the word makes physicists nervous is that it can be misleading in public discussions. When people hear infinite density or point of infinite mass, they often imagine something physically real and concrete, like a tiny super heavy object sitting at the center of the black hole. But infinity is not a physical quantity in the same way that mass, length, or time is. You cannot measure infinity. You cannot put it on a scale. When it appears in an equation, it is often a sign that the equation has gone beyond what it was designed to handle. This does not mean that nothing is there. It means that we do not yet have the right language to describe what is there. Some physicists prefer to talk about the core or interior of a black hole without committing to the idea of a singular point. Others emphasize that the singularity is a feature of the mathematical solution, not necessarily a feature of the physical world. There is also a technical detail that adds nuance to the discussion. Not all singularities in general relativity are the same. Some are what physicists call coordinate singularities. These are places where the math looks like it is blowing up, but the problem is actually with the way the coordinates are chosen, not with the underlying geometry. The classic example is the event horizon itself. In the original mathematical description of a non-rotating black hole, the equations seemed to become infinite at the horizon. For a while, people thought this might mean something physically dramatic happened there. Later, it was shown that this was just a coordinate issue. By choosing a different way of labeling points in space-time, the apparent infinity disappeared, and the horizon turned out to be a perfectly ordinary place locally. The singularity at the center, however, does not go away when you change coordinates. It appears to be a more fundamental feature of the solution. That makes it more serious, but it also makes it more likely that a deeper theory is needed to understand it. This brings us to the ongoing effort to develop a theory of quantum gravity, a framework that combines general relativity and quantum mechanics into a single, consistent picture. There are several approaches to this, including string theory, loop quantum gravity, and others. One of the things these approaches often have in common is that they tend to smooth out singularities. Instead of a point of infinite density, they predict a region of extremely high but finite density, or a new kind of structure altogether. For example, in some versions of loop quantum gravity, space-time is not continuous, but made up of tiny discrete units, something like atoms of space. In this picture, there is a smallest possible volume which prevents true infinities from forming. The collapse inside a black hole might reach this minimum scale and then change behavior, perhaps even leading to a kind of bounce. In some string theory models, the fundamental building blocks of reality are not points, but tiny extended objects. This can also soften the extreme behavior predicted by point-based theories, replacing singularities with more spread-out structures. These ideas are still being developed, and none of them has been confirmed by direct experiment. But they illustrate a common theme. When physicists look at a singularity, they do not usually see a final answer, they see a challenge. There is also a conceptual discomfort with the idea of a true singularity, because it seems to break the link between cause and effect. If everything is crushed into a single point, what does it mean for one thing to influence another? How does time behave in such a place? Does it even make sense to talk about before and after? In general relativity, time and space are part of the same fabric. At a singularity, that fabric is said to be infinitely curved. The usual distinction between space and time can blur. This makes it hard to apply our everyday notions of sequence and change. Some researchers argue that this is another sign that the singularity is not a physical object, but a breakdown in the way we are trying to describe the situation. They suggest that a more complete theory would restore a meaningful sense of structure and evolution, even in the deepest interior of a black hole. There is also an observational side to this nervousness. The event horizon hides the interior of a black hole from the outside universe. That means, in practice, we cannot directly test what is happening near the supposed singularity. We can make theoretical predictions, but we cannot send a probe in and get data back. This lack of direct access makes it especially important to be cautious about taking mathematical results too literally. Without observational confirmation, it is harder to know whether a feature of a model corresponds to something physically real. This does not mean the models are useless. On the contrary, they have been incredibly successful at describing everything we can observe outside the horizon. It simply means that the region inside remains a place where theory outpaces evidence. There is a kind of humility built into this attitude. Instead of declaring that the universe contains a literal point of infinite density, many physicists prefer to say, "This is where our current description stops." That phrasing leaves room for future ideas. It also connects to a broader pattern in the history of science. Many of the biggest advances have come from places where existing theories broke down. The edges of understanding are often where the most interesting questions live. In that sense, the singularity is less like a destination and more like a signpost. It marks a place where the road we are on ends, not because the landscape ends, but because the map does. From a more philosophical perspective, there is something almost comforting about this. It suggests that the universe is not fully captured by any single framework. There is always more to learn, more to refine, more to explore. The word singularity, then, becomes a reminder of that openness. It points to a region of mystery, but not necessarily to a region of impossibility. There is also a practical aspect to this nervousness that shows up in how physicists talk to each other. In research papers and conferences, the word is often used carefully, with qualifications and context. It is not usually presented as a simple, literal description of what exists inside a black hole, but as a feature of a particular solution to a set of equations. This careful language reflects an awareness of how easily the idea can be misunderstood. It is a way of keeping the door open to alternative interpretations. As you sit with this, notice how the tone shifts from the dramatic to the thoughtful. The singularity, instead of being a terrifying point of infinite destruction, becomes a place where our knowledge becomes thin and our questions become more pointed. It is a place that invites patience rather than panic. This perspective also aligns with a broader theme of this journey, that the black hole itself is a well-defined physical object with clear, measurable properties, while the singularity is a feature of our current theoretical description, one that may change as our understanding deepens. The distinction matters because it shapes how we think about the limits of science. If the singularity is real in a literal sense, then there may be places in the universe that are fundamentally beyond explanation. If it is a placeholder for a better theory, then those places are not beyond understanding, just beyond our current reach. The nervousness around the word singularity is not a sign of fear, but of care. It reflects a deep respect for the difference between what our theories say and what the universe actually does. The singularity sits at the edge of that difference, a small, heavy word that carries a large question, and as long as that question remains open, it continues to draw attention, curiosity, and the slow, steady effort to understand what lies just beyond the boundaries of our current maps. Somewhere between the neat rows of symbols on a chalkboard and the quiet motion of stars in the night sky, there is a subtle shift that happens when our mathematical descriptions begin to lose their confidence. The equations do not stop. They still produce answers, but those answers start to feel less like clear statements and more like hints, less like firm ground and more like a soft edge where certainty thins out. This is the place we arrive at when we talk about black holes and the deep interior that our best theories can gesture toward but not fully describe. To understand what it means for equations to whisper, it helps to remember what they usually do. In most areas of physics, an equation is a kind of promise. You put in information about a system, and it tells you how that system will behave. If you know the position and speed of a planet, you can predict where it will be tomorrow. If you know the properties of a circuit, you can predict how current will flow. There is a satisfying sense of cause and effect, a feeling that the world, while complex, is still legible. General relativity, the theory that gives us black holes in the first place, is one of the most successful examples of this kind of promise. Its equations describe how mass and energy shape space-time, and how that curved space-time guides the motion of matter and light. With them, physicists can calculate the bending of light near the sun, the slow drift of Mercury's orbit, the expansion of the universe, and the ripples in space-time created by colliding black holes. Over and over, observation has confirmed the predictions. But every map has edges, and every theory has a range where it works best. When you push general relativity toward the center of a black hole, something interesting happens. The calculations become extreme. Quantities like curvature, density, and tidal force grow larger and larger. Eventually, they reach values that the math represents as infinite. At that point, the equations are still producing output, but the output stops being physically meaningful in the usual way. Infinity is not something you can measure or observe. It is not a number you can compare to anything else. It is a sign that the model is being asked a question it cannot answer in its current form. This is what it means for the equations to whisper. They're telling you that you have reached the boundary of their authority. To make this more concrete, consider a simpler example from everyday mathematics. Take a function like 1 divided by x. As x gets smaller and smaller, approaching 0, the value of the function gets larger and larger. At x equals 0, the function is undefined. The math does not tell you what the value is there, it simply stops. That does not mean there is a physical object with an infinite value at that point. It means the particular way you chose to describe the situation is no longer appropriate. In the case of black holes, general relativity is like that function. It describes space-time as a smooth, continuous fabric. It assumes that you can zoom in as far as you like and still talk about points, distances, and curvature in the same way. Near the center of a black hole, those assumptions may no longer hold. Quantum mechanics, which governs the behavior of matter and energy at very small scales, suggests that there are limits to how finely you can divide space and time. There may be a smallest meaningful length, a smallest meaningful duration. If that is true, then the idea of a perfectly smooth, infinitely divisible space-time breaks down. When you apply a theory built on smoothness to a situation where discreteness might matter, it is not surprising that the results become strange. This tension between smooth and discrete descriptions sits at the heart of why the equations begin to whisper near a singularity. General relativity wants to treat space-time like a continuous surface. Quantum mechanics wants to treat reality as something that comes in packets, with built-in limits to how precisely things can be defined. So far, no single theory successfully combines these two perspectives in a complete, tested way. Physicists can work with them separately, each in its own domain, but in the extreme environment inside a black hole, both sets of rules are likely to be important at the same time. This is where the whispering starts to sound like a call for a new language. Another way to see this is to look at how predictions behave as you move inward. Far from the black hole, you can calculate orbits, light paths, and time dilation with confidence. The results are stable and well behaved. As you approach the horizon, the math becomes more intricate, but it still works. You can track how signals redshift, how clocks slow, how paths curve. Beyond the horizon, the structure of the equations changes. In the standard description, the roles of space and time swap in a certain sense. The direction that used to be forward in time becomes inward in space. This is not just a poetic statement. It shows up directly in the mathematical form of the solutions. In that region, moving toward the center is as inevitable as moving into the future is in everyday life. You cannot stop it. You cannot turn around. The equations still describe this process, but the way they do it starts to feel more formal than intuitive. Then, as you push all the way to the center, the quantities that describe curvature and density diverge. The equations do not tell you what space-time looks like there. They tell you that their own assumptions have failed. There is something almost self-aware about that. The math is not pretending to know more than it does. It is signaling that you have reached a limit. Physicists have a term for this kind of situation. They call it a breakdown of the theory. That does not mean the theory is wrong in the domains where it works. It means it is incomplete. It is missing ingredients that become important under certain conditions. In the case of black holes, the missing ingredient is almost certainly a full understanding of how gravity behaves at quantum scales. This realization has driven decades of work on quantum gravity. Researchers have proposed many different approaches, each with its own way of rethinking space, time, and matter. Some approaches suggest that space-time itself is made of tiny building blocks, something like a network or a lattice. In this view, the smooth fabric of general relativity is an approximation that works well at large scales, but at very small scales the structure becomes granular. If that is true, then the idea of infinite curvature loses its meaning. There is a maximum curvature set by the smallest possible building blocks. Other approaches imagine that the fundamental ingredients of reality are not points, but extended objects, like tiny strings. In that picture, interactions that would be infinitely sharp in a point-based theory become spread out over a small but finite region. Again, the infinities soften. There are also ideas that treat space-time as something that emerges from more basic relationships, such as patterns of entanglement between quantum systems. In these models, space and time are not fundamental at all. They arise from deeper structures. A singularity in that context might not be a place where space-time becomes infinite, but a place where the very notion of space-time ceases to be the right way to talk about what is happening. All of these ideas share a common motivation. They take the whispering of the equations seriously. They treat it as a message that the current framework is being stretched beyond its design. This is not a sign of failure. It is how progress often begins. There is a human parallel here that can make the abstract feel more grounded. Think about learning a new language. At first, you can express simple ideas clearly. As you try to talk about more complex or subtle things, you may find yourself searching for words, using gestures, or speaking around the idea rather than stating it directly. Your language starts to whisper. It hints instead of declaring. That does not mean the idea you're trying to express is meaningless. It means your current vocabulary is not yet rich enough to capture it. In physics, equations are our vocabulary. When they whisper, it means the universe is asking us to expand that vocabulary. There is also an emotional side to this that is easy to overlook. Much of science is built on the comfort of predictability. The ability to say, if this, then that, gives a sense of stability and control. When a theory reaches a point where it cannot make clear predictions, that comfort fades. But in its place, something else can appear, a sense of openness. The unknown is not just a gap, it is a space for new ideas. The interior of a black hole, as described by our current equations, is such a space. We can draw diagrams, we can write down solutions, we can talk about horizons and singularities. But when we look closely, we see that these descriptions are provisional. They depend on assumptions that may not hold in the most extreme conditions. This awareness changes how physicists talk about what lies inside. Instead of making bold claims about what is there, they often frame their statements carefully. They speak in terms of models, possibilities, and what the math suggests, rather than what is definitively the case. That careful tone is another form of whispering. It also reflects the fact that, for now, the interior of a black hole is not directly accessible to observation. We can test our theories against what happens outside the horizon. We can measure masses, spins, and the behavior of surrounding matter. We can detect gravitational waves from mergers, but we cannot send a signal from inside and read the results. This lack of direct feedback makes the role of theory even more important, and it makes the limits of theory even more significant. There is a subtle balance here between confidence and humility. On the one hand, the success of general relativity and quantum mechanics in their respective domains gives physicists reason to trust their tools. On the other hand, the appearance of singularities and infinities is a reminder that those tools are not the final word. This balance is part of what keeps the field moving forward. It encourages both careful testing of existing ideas and bold exploration of new ones. As you sit with this, you might notice how different this picture is from the way science is often portrayed in popular culture. There, it is sometimes shown as a march toward absolute answers, a steady replacement of mystery with certainty. The reality is more like conversation. Each theory answers some questions and raises others. Each success reveals new edges where understanding becomes thin. The black hole, with its whispering equations, sits right at one of those edges. There is also a sense in which this whispering is not limited to black holes. Similar things happen at the very beginning of the universe, when we run our equations backward to the Big Bang. There too we encounter a singularity, a place where densities and temperatures become infinite in the math. Again, many physicists interpret this not as a literal, physical infinity, but as a sign that a deeper theory is needed to describe the earliest moments of the cosmos. This parallel between the center of a black hole and the origin of the universe is one of the more intriguing connections in modern physics. It suggests that the same missing piece of understanding might be needed to describe both extremes, the very small and the very large. Some researchers even explore the idea that what we call a singularity is not an endpoint, but a transition. In certain models, the collapse inside a black hole leads to a new expanding region of space-time, something like a baby universe. In others, the Big Bang itself is seen as a kind of bounce from a previous contracting phase. These ideas are speculative, but they show how the whispering of the equations can inspire imaginative and far-reaching possibilities. There is a gentle irony in all of this. Black holes are often thought of as the ultimate expressions of gravity, the places where it is strongest and most dominant. Yet it is precisely in these places that our understanding of gravity becomes most uncertain. The thing we thought we understood best is what leads us to a point where understanding becomes most fragile. This does not diminish the power of the theory. It highlights its depth. A shallow theory might fail quickly. A deep one can take you very far before it begins to strain. The math does not shout or break. It keeps working until it reaches a place where it can no longer speak clearly. At that point, it does something more subtle. It hints. It suggests. It invites a new way of listening. And in that invitation, there is a sense of continuity rather than finality. It changes tone, opening up a space for new questions, new frameworks, and a deeper exploration of what the universe might be doing in the places where our current language fades into quiet. At first glance, infinity can feel like a powerful and almost comforting idea. It suggests something without limits, something that never runs out, something that stands beyond all boundaries. In everyday conversation, we use the word loosely to describe anything that feels very large, very long, or very intense. But in physics, infinity carries a very different tone. It is not usually a sign of completion or success. More often, it is a warning light, a signal that a description of the world has been pushed past the point where it can still make reliable sense. To ease into this idea, it helps to think about what a physical theory is meant to do. At its core, a theory is a structured way of connecting what we observe to what we expect to happen next. It gives you a set of rules that link causes to effects. If you know the state of a system now, the theory tells you how it will change over time. There is a quiet satisfaction in that kind of predictability, a sense that the universe, even in its complexity, is following a script that can be read. Infinity interrupts that script. When an equation produces an infinite value for something that is supposed to be physical, like density, temperature, or curvature, it is no longer telling you how the system behaves. It is telling you that the language you're using has reached a place where it cannot describe what is happening. The number is not just large. It is undefined in a way that breaks the connection between cause and effect. This is why physicists tend to treat infinities with suspicion. They are not usually taken as literal features of the world. They are taken as signs that something important is missing from the description. A simple way to see this is to return to mathematics for a moment. Consider dividing by 0. If you take a number and divide it by smaller and smaller values, the result gets larger and larger. As the denominator approaches 0, the result approaches infinity. At exactly 0, the operation stops making sense. The math does not give you a meaningful answer. It gives you a signal that you have asked an invalid question within that particular framework. In physics, something similar happens when a theory predicts that a measurable quantity becomes infinite. The theory is effectively saying, I do not know how to go further from here. This perspective changes the emotional weight of the word infinity. Instead of being a grand, almost mystical concept, it becomes a practical marker of a theory's limits. One of the earliest and most famous examples of this in modern physics came from the study of light and heat. At the end of the 19th century, scientists were trying to understand how hot objects emit radiation. Classical physics predicted that as you look at shorter and shorter wavelengths of light, the amount of energy emitted should increase without bound. The math led to an infinite total energy output. This result was clearly wrong. Objects do not radiate infinite energy. The problem was not with the universe. The problem was with the theory. The resolution came with the introduction of quantum mechanics, which changed the way energy and light were described. Energy could only be exchanged in discrete packets, not in a smooth, continuous flow. This new idea removed the infinity from the calculations and produced results that matched what was observed. In this case, the appearance of infinity was not a final truth. It was a clue. Another example appears in the early understanding of the atom. Classical physics treated electrons as tiny charged particles orbiting a nucleus, like planets around a star. According to the equations, these electrons should radiate energy as they move, gradually losing speed and spiraling into the nucleus. This would lead to a collapse of the atom. Once again, this does not happen in reality. Atoms are stable. The theory was missing something. Quantum mechanics provided the missing piece by introducing the idea that electrons occupy specific states rather than following classical orbits. This new framework eliminated the problem and restored stability to the picture of the atom. These historical examples shape how physicists respond when they encounter infinities in their equations today. They see them as invitations to look for a deeper or more complete description. Now bring this mindset back to black holes and the singularity at their center. In the equations of general relativity, as you move inward, the density of matter and the curvature of space-time grow larger and larger. At the center, they become infinite. If taken literally, this would mean that a finite amount of mass is compressed into a point with zero volume, creating an object of infinite density. This idea is mathematically neat, but physically troubling. For one thing, it clashes with the way quantum mechanics treats matter and energy. Quantum theory suggests that there are limits to how precisely you can define both position and momentum. There are also hints that there may be a smallest possible length scale, often associated with the Planck length. If such a minimum exists, then the idea of a point with zero volume loses its meaning. There is also the issue of energy. To compress matter into an infinitely small space, you would need to deal with energies that go beyond anything we can currently describe. The very concepts of space and time might stop behaving in recognizable ways. This does not mean that nothing extreme happens inside a black hole. It means that the word infinite is likely not the right way to describe it. Another place where infinity appears in our current theories is at the beginning of the universe. When cosmologists run the equations of general relativity backward in time, they find that the universe appears to have started from a state of infinite density and temperature. This Big Bang singularity is, in many ways, similar to the one predicted at the center of a black hole. In both cases, the math leads to a point where the theory can no longer say what happens. Many physicists suspect that, just as with black holes, this is a sign that general relativity is being pushed beyond its range of validity. The early universe was so small and so energetic that quantum effects should have played a major role. A complete theory of quantum gravity might replace the initial singularity with something else. Perhaps a very hot, very dense but still finite state, or even a bounce from a previous phase of contraction. This pattern reinforces the idea that infinity often marks the boundary between what we can describe and what we cannot, rather than a literal feature of reality. There is also a conceptual reason why physicists are uneasy with infinities. Much of the power of a physical theory comes from its ability to make predictions. If a quantity becomes infinite, predictions become impossible. Imagine trying to calculate the motion of an object if the force acting on it is infinite. The equations that link force, mass, and acceleration stop working. There is no meaningful way to say what will happen next. In the context of a black hole singularity, this can lead to a breakdown of determinism. If the laws of physics cannot tell you how things evolve at or beyond that point, then the chain of cause and effect becomes unclear. For a field that has been built on the idea that the universe follows consistent rules, this is deeply uncomfortable. It suggests that there are places where the rules simply stop. Many physicists prefer a different interpretation. They suspect that the rules do not stop. Our current description does. This brings us to the ongoing search for a theory that can handle both gravity and quantum mechanics at the same time. The goal of quantum gravity is to create a framework that works in the extreme environments where both sets of effects are important. In such a framework, the infinities that appear in general relativity might be replaced by finite, well-defined quantities. Some approaches suggest that space-time itself is made of discrete elements, something like tiny building blocks. In this picture, there is a smallest possible volume, which prevents densities from becoming infinite. The collapse inside a black hole might reach this minimum scale and then behave in a new way. perhaps stabilizing or transitioning into a different state. Other approaches propose that the fundamental ingredients of reality are extended rather than point-like. Instead of treating particles as mathematical points, they are treated as tiny strings or loops. This spreads interactions over a small but finite region, smoothing out the sharp peaks that would otherwise lead to infinities. There are also ideas that treat space and time as emergent properties, arising from more basic relationships between quantum systems. In these models, a singularity might represent not a place where something becomes infinite, but a place where the concepts of space and time themselves stop being the right tools for description. What these ideas have in common is a refusal to accept infinity as a physical endpoint. They treat it as a signpost, pointing toward a deeper level of structure. There is a practical side to this as well. Theories that produce infinities are often difficult to work with. Calculations become unstable. Small changes in input can lead to wildly different outputs. This makes it hard to connect theory with observation. Physicists have developed techniques to manage this, such as renormalization in quantum field theory, where certain infinities are systematically removed or absorbed into redefined quantities. This process does not eliminate the underlying issue, but it allows the theory to make accurate predictions in the domains where it has been tested. The success of these techniques reinforces the idea that infinities are not physical objects. They are artifacts of the way a theory is formulated. Another subtle point is that infinity often arises when a model assumes something can be perfectly smooth or perfectly sharp. In the real world, perfect smoothness and perfect sharpness are rare. Surfaces have texture, signals have noise, measurements have limits. In the case of space-time, general relativity assumes a perfectly smooth fabric. Quantum mechanics suggest that at very small scales this smoothness may break down. If space-time has a kind of microscopic structure, then the idea of infinite curvature at a single point might be replaced by a very large but finite curvature spread over a small region. This shift from point-like to region-like thinking is a common theme in attempts to move beyond singularities. There is also a philosophical layer to this discussion. Infinity is a concept that humans have developed to talk about unbounded processes and quantities. It is a powerful idea, but it is also an abstract one. When we apply it to the physical world, we are making a claim that something exists that cannot be measured, cannot be compared, and cannot be fully described. Some physicists are comfortable with that, others are more cautious. The cautious view is that physics should deal with things that, at least in principle, can be related to observation. An infinite value does not meet that criterion. This does not mean that infinity has no place in physics at all. It can be a useful tool in mathematics. It can help describe limits and idealizations. But when it shows up as a literal prediction about a physical quantity, it often signals a deeper issue. The story of black holes brings this tension into sharp focus. On the one hand, the equations that predict singularities are part of a theory that has passed every experimental test we have been able to perform. On the other hand, the singularity itself lies in a region we cannot observe directly, and where the theory's assumptions are most questionable. This combination of success and uncertainty makes the appearance of infinity both intriguing and unsettling. It is also what keeps the topic alive. If the equations simply stopped at the event horizon and refused to say anything about the interior, the problem might be easier to set aside. The fact that they go further and then break down invites attention. It is like following a trail that leads to a cliff. The trail itself is well marked and reliable. The cliff is not the end of the world, but it is the end of the path as currently drawn. Standing there, you can look out and imagine what might lie beyond, even if you cannot step forward yet. This image captures something of how physicists think about singularities and infinity. The trail of general relativity leads to a point where the landscape becomes unknown. The appearance of infinity marks that edge. There is also a connection here to how we, as individuals, relate to limits in our own understanding. There are questions we can answer, skills we can master, And then there are areas where our knowledge becomes thin. Reaching those edges does not mean that reality ends there. It means our current tools have taken us as far as they can. In that sense, infinity is not a wall. It is a horizon of its own, marking the boundary between what we can currently describe and what we are still learning how to talk about. Before we step too deeply into the places where understanding begins to thin, it helps to pause and take stock of what one of our most powerful ideas actually gives us. Albert Einstein's theory of general relativity is often spoken about with a kind of quiet reverence, and for good reason. It has reshaped how we think about space, time, motion, and gravity. It has predicted phenomena that were later observed with remarkable precision. Yet even this elegant framework has its boundaries. There are questions it answers beautifully and questions it can only gesture toward before falling silent. To appreciate both sides of this, it is worth returning to the core idea of the theory itself. General relativity replaces the older notion of gravity as a force with a geometric picture. Mass and energy tell space-time how to curve, and that curved space-time tells matter and light how to move. Instead of being pulled by an invisible hand, objects follow the straightest possible path through a landscape that has been shaped by everything else in it. This shift may sound abstract, but its consequences are deeply tangible. It explains why time runs a little slower closer to Earth's surface than it does in orbit. It accounts for the bending of light around stars and galaxies. It predicts the slow dance of planets and the grand expansion of the universe itself. Over and over, experiments and observations have confirmed its predictions, often to astonishing levels of accuracy. One of the clearest demonstrations of its power came with the detection of gravitational waves. When two massive objects like black holes spiral toward each other and merge, they send ripples through space-time. These ripples were predicted by Einstein's equations a century before they were finally observed. When detectors on Earth picked up those faint signals, it was as though the theory had reached across time to say, yes, this is how the universe moves. In the context of black holes, general relativity shines especially brightly. The very idea of a black hole emerges naturally from the equations. Given enough mass packed into a small enough region, the geometry of space-time becomes so curved that an event horizon forms, a boundary beyond which light cannot escape. The theory tells us how big that horizon should be for a given mass. It tells us how objects and light behave near it. It tells us how two black holes orbit and merge, and what kind of gravitational waves that merger will produce. These predictions have been tested by observing the motion of stars near the center of our galaxy, by measuring the light from hot gas swirling around distant black holes, and by listening to the faint echoes of space-time itself. In all of these areas, the theory speaks clearly. It also offers a surprisingly simple description of black holes themselves. Despite all the complexity of what can fall in, a black hole in general relativity is characterized by just a few numbers: its mass, its spin, and its electric charge. This simplicity is sometimes summarized by saying that black holes have no hair, meaning no extra distinguishing features. The details of what went into them are, from the outside, largely erased. This aspect of the theory is powerful because it allows physicists to make precise predictions about how black holes should behave in many situations. It also connects black holes to broader principles in physics, such as conservation laws and thermodynamics. Yet even as general relativity provides this clear, structured picture, there are places where its voice becomes softer. One of those places is the interior of a black hole. The equations can be extended beyond the event horizon. They describe how space-time continues to curve inward. They suggest that, for an object falling in, the direction toward the center becomes as unavoidable as the direction toward the future. But when you follow those equations all the way to the center, they predict a singularity, a point where curvature and density become infinite. At that point, the theory does not give a meaningful description of what space-time looks like or how matter behaves. This is not just a technical detail, it marks a fundamental limit. The theory can tell you that something extreme happens, but it cannot tell you what that something is in physical terms. Another place where the theory begins to strain is in its relationship with quantum mechanics. General relativity is a classical theory. It treats space-time as a smooth, continuous entity. Quantum mechanics, by contrast, describes a world that is grainy, probabilistic, and full of inherent uncertainty. In everyday situations, this difference does not matter much. The gravitational fields we encounter are weak enough, and the scales we deal with are large enough, that quantum effects can be ignored. The two theories can coexist without conflict. Inside a black hole, or at the very beginning of the universe, that separation breaks down. The densities and energies involved become so high that both gravitational and quantum effects should be important at the same time. In these regimes, we do not yet have a theory that consistently combines both sets of rules. This means that while general relativity can take us a long way toward describing what happens, it cannot provide the full story in the most extreme environments. There is also the issue of time. In general relativity, time is not an external universal parameter. It is part of the fabric of space-time and can be stretched or compressed by gravity and motion. This leads to effects like time dilation, where clocks run at different rates in different gravitational fields or at different speeds. The theory handles these effects with elegance. It gives precise formulas for how time should behave in various situations. These formulas have been tested by experiments with atomic clocks on airplanes and satellites. But when you approach a singularity, the concept of time itself becomes difficult to define. The equations suggest that all possible futures lead to that point. The usual idea of a timeline, a sequence of moments that can be ordered and measured, begins to lose its clarity. This raises deep questions about what it even means to talk about what happens at a singularity. If time, as we understand it, stops being well defined, then the language of before and after may no longer apply in the usual way. Another limitation shows up in the way general relativity treats energy. In many areas of physics, energy is something you can define locally. You can talk about the energy density at a particular point in space. In general relativity, because space-time itself is dynamic, defining a local energy density for the gravitational field is not straightforward. This makes certain kinds of calculations more subtle. It also reflects a broader theme that the theory reshapes some of our most basic concepts, including space, time, and energy, in ways that can make them harder to pin down. There is also a practical limitation in how the theory is tested. We can observe black holes from the outside. We can measure their effects on nearby stars and gas. We can detect gravitational waves from their mergers, but we cannot observe the interior directly. This means that while the theory's predictions about horizons and exterior behavior can be tested, its predictions about the singularity and the deep interior remain in the realm of inference. This gap between what can be tested and what is purely theoretical is another place where the theory's voice becomes quieter. It is not that the equations stop, it is that their connection to observation becomes thinner. There are also subtle questions about how general relativity handles information. According to the theory, once something crosses the event horizon, it is lost to the outside universe. But quantum mechanics suggests that information should be conserved. This tension has led to decades of discussion and debate. It has inspired ideas about information being encoded on the horizon, about subtle correlations in Hawking radiation, and about deeper principles that might reconcile the two views. Here again, general relativity provides part of the picture, but not all of it. It is also worth noting that the theory is highly sensitive to its own assumptions. It assumes that space-time is a smooth, differentiable manifold. It assumes that the equations of motion can be applied at all scales. These assumptions work extremely well in the regimes we can test. Whether they remain valid at the smallest possible scales is an open question. This brings us back to the idea of maps and territories. General relativity is an extraordinarily detailed and accurate map of the gravitational landscape. It covers vast regions with clarity. It guides us through the motions of planets, the life cycles of stars and the structure of galaxies. But like any map, it has edges. Near those edges, the symbols become less clear and the scale becomes harder to interpret. One of the strengths of the theory is that it tells us where those edges are. The appearance of singularities and infinities is not just a problem, it is also a signpost. It marks the places where new ideas are needed. This is why black holes are such a central focus in the search for a deeper theory of gravity. They bring together the extremes of mass, density, and curvature in a way that pushes our current framework to its limits. They are, in a sense, natural laboratories for testing the boundaries of our understanding. There is a quiet beauty in that. The same theory that describes the gentle bending of light near the sun also leads us to the edge of knowledge in the heart of a black hole. The same set of equations connects the everyday and the extreme. This continuity is part of what makes general relativity so compelling. It is not a patchwork of separate rules for different situations. It is a unified framework that stretches across scales, from the motion of a falling apple to the dance of colliding galaxies. At the same time, the places where it begins to falter remind us that unification is not complete. There is more to the story. Some physicists see this as a kind of invitation. The theory has taken us far. Now it is pointing toward what comes next. In the search for that next step, researchers explore many different directions. Some focus on quantizing space-time itself, treating it as something that can be described in terms of quantum states. Others look for deeper symmetries that might unify gravity with the other fundamental forces. Still others explore the idea that space-time and gravity might emerge from more basic non-geometric structures. Each of these approaches is, in its own way, an attempt to give the equations a stronger voice in the places where they currently whisper. There is also a cultural aspect to how Einstein's theory is perceived. It has become a symbol of deep understanding, of a kind of intellectual triumph over the complexities of the universe. This can make it tempting to treat it as final. But the history of science suggests that even our most successful theories are often stepping stones rather than endpoints. Newton's laws were once seen as the ultimate description of motion and gravity. They still work beautifully in many contexts, but they were eventually shown to be part of a larger picture. General relativity may occupy a similar place. It may be a remarkably accurate approximation to a deeper, more comprehensive theory. This perspective does not diminish its achievements. It places them in a larger narrative of ongoing discovery. As you let this idea settle, notice how it changes the way the theory feels. Instead of being a finished monument, it becomes a living framework, one that continues to guide research and inspire new questions. The black hole, with its horizon and its singularity, sits right at the intersection of what the theory can say clearly and what it cannot. It is both a triumph of prediction and a challenge to understanding. That dual role is part of what makes it such a compelling subject. There is also a more personal, almost reflective aspect to this. The idea that even our best explanations have limits can be both humbling and freeing. It reminds us that understanding is not about reaching a final answer, but about continually refining our questions. In that sense, the quiet places where Einstein's theory falls silent are not empty. They are full of possibility. For now, it is enough to appreciate the balance that general relativity offers. It speaks with clarity about the structure of space-time, the behavior of light and matter, and the nature of gravity across much of the universe. It also, in its own way, points to the places where a deeper understanding is still waiting to be found. Imagine for a moment that instead of drawing a tiny dot on a page to represent the center of a black hole, you're asked to describe a room you cannot enter, using only the way the air feels near the doorway. That is closer to what physicists are doing when they talk about the interior of a black hole, without relying on the idea of an imaginary point of infinite density. They are not peering directly inside. They are inferring, modeling, and carefully extending what they know from the outside, guided by the way their equations behave as they approach the boundary. This way of thinking shifts the focus away from a single, dramatic spot at the center and toward the structure of the region as a whole, instead of asking what is the point where everything ends. The question becomes, what kind of place is this interior if our current maps are only approximations? To begin exploring that, it helps to recall how the standard picture arises in the first place. In general relativity, a black hole forms when a large amount of mass collapses into a small enough region that an event horizon appears. If you follow the mathematical description inward, the equations predict that spacetime curvature increases without bound, leading to a singularity. That prediction depends on treating spacetime as a smooth, continuous fabric that can be bent arbitrarily sharply. It also depends on treating matter as something that can be compressed into an arbitrarily small volume. Both of these assumptions work well in many situations, but both are questionable when you reach extreme conditions. So what happens if you relax those assumptions? One of the simplest alternatives is to imagine that there is a limit to how much spacetime can curve and how tightly matter can be packed. This limit might come from quantum mechanics, which already places constraints on how precisely you can know the position and momentum of a particle at the same time. If there is a smallest meaningful length scale, then the idea of a perfectly sharp point becomes less natural. In this view, the interior of a black hole would not end in a point. Instead, it would contain a region of extremely high but finite density and curvature. The math would describe a steep, deep well rather than a bottomless pit. This shift changes the emotional tone of the interior. It becomes less like a cliff and more like a valley. Still extreme, still far beyond everyday experience, but not defined by an abstract infinity. Some approaches to quantum gravity make this idea more concrete. In loop quantum gravity, for example, space-time is treated as being made up of tiny, discrete elements. These are not particles in the usual sense, but fundamental units of area and volume. In such a framework, there is a smallest possible chunk of space. If that is true, then as matter collapses inside a black hole, it cannot be compressed into something smaller than that minimum volume. The collapse would slow down and change character as it approached this scale. Instead of forming a singularity, the interior might reach a state of maximum density and then do something else. One possibility is that it could undergo a kind of bounce, where the inward collapse transitions into an outward expansion. This does not necessarily mean that matter shoots back out into the same universe. In some models, the bounce leads to the formation of a new, separate region of spacetime, sometimes described as a baby universe. This idea is speculative, but it illustrates how thinking beyond imaginary points opens up a different set of possibilities. The interior of a black hole becomes a place where new structures can form, rather than a place where structure is destroyed. Another approach comes from string theory, which suggests that the fundamental building blocks of reality are not point-like, but extended objects, tiny strings that can vibrate in different ways. Because these objects have a finite size, interactions that would be infinitely sharp in a point-based theory become spread out. In such a picture, the center of a black hole might not be a single point, but a complex, tangled region of these fundamental strings and other higher dimensional objects. The density and curvature could still be enormous, but they would be distributed over a finite volume. This again replaces the idea of a singular point with the idea of a small but structured region. There are also ideas that treat spacetime itself as something that emerges from deeper relationships between quantum systems. In these models, space and time are not fundamental. They arise from patterns of entanglement and information. From that perspective, the interior of a black hole is not a place in the usual sense. It is a different kind of arrangement of information. The center is not a location you can point to. It is a feature of how the underlying quantum relationships are organized. This way of thinking can feel abstract, but it has a practical motivation. If space and time are emergent, then asking what happens at a point where space and time break down might be like asking what happens at a point where a language stops being applicable. The question itself needs to be reframed. Another important idea in this area is the notion that the interior of a black hole might be less isolated from the outside universe than it appears. According to the holographic principle, the information about what falls into a black hole could be encoded on its event horizon. If that is the case, then the interior might be fully described by what is happening at the boundary. The inside becomes, in a sense, a different way of organizing information that is also present on the surface. This does not eliminate the interior. It changes how it is understood. Instead of being a hidden volume with its own independent contents, it becomes a representation of something that is already encoded elsewhere. There are even ideas suggesting that the interior geometry might be related to patterns of entanglement in the quantum fields outside the black hole. In this view, the shape of space inside is linked to how different parts of the outside world are correlated with each other. This kind of connection blurs the line between inside and outside. The boundary becomes not just a separator, but a bridge between two ways of describing the same underlying reality. All of these ideas share a common theme. They move away from the notion of a single imaginary point where everything ends. They replace it with regions, structures, and relationships. That shift has practical consequences for how physicists think about problems like the fate of information. If there is no singular point where information is destroyed, then there is room for it to be preserved in some form, even if it is scrambled beyond easy recognition. It also changes how we think about time inside a black hole. In the standard picture, all future-directed paths lead to the singularity. Time, in a sense, runs into a wall. If the singularity is replaced by a region or a bounce, then time might continue in some form. The notion of after does not necessarily disappear. It just becomes part of a different structure. This is not to say that the interior becomes a comfortable or familiar place. The conditions would still be extreme beyond anything we can directly experience. The densities, energies, and curvatures involved would dwarf those in any laboratory. But the idea that there is structure rather than an abstract infinity makes the situation feel more like a physical environment and less like a mathematical glitch. There is also an observational angle to this discussion. While we cannot see inside a black hole, we can study how black holes form and how they interact with their surroundings. In particular, the way a black hole rings down after a merger, producing a characteristic pattern of gravitational waves, depends on its internal structure. If the interior were radically different from what general relativity predicts, it might leave subtle imprints on these signals. Researchers are looking for such effects, searching for tiny deviations from the expected patterns. So far, the observations are consistent with the predictions of general relativity. That does not rule out alternative interiors. It simply means that any differences must be subtle, at least at the scales we can currently probe. This careful, incremental approach is typical of how physics advances. Bold ideas are proposed, but they are always measured against what can be observed. There is also a conceptual comfort in thinking about interiors without imaginary points. It aligns with a broader pattern in science, where sharp, idealized features are often replaced by smoother, more realistic ones as understanding deepens. In fluid dynamics, for example, early models treated fluids as perfectly continuous and smooth. At very small scales, this breaks down, and the discrete nature of molecules becomes important. The smooth model is still useful, but is recognized as an approximation. The same may be true of space-time. General relativity treats it as smooth and continuous. Quantum gravity may reveal a finer structure beneath that smoothness. If so, the singularity is like a place where the smooth approximation fails. Another way to think about this is in terms of resolution. When you look at a digital image from far away, it looks smooth. As you zoom in, you start to see individual pixels. If you zoom in further, the image no longer makes sense as a picture of a scene. It becomes a pattern of coloured squares. Space-time, in this analogy, might look smooth at large scales, but pixelated at very small scales. The singularity is the place where you have zoomed in so far that the smooth picture no longer applies. This analogy helps capture why the idea of an imaginary point can feel unsatisfying. It is like insisting that the picture must keep getting smoother and more detailed as you zoom in, even when the underlying structure is discrete. There is also a subtle shift in how we think about causality when we move away from singular points. In the standard picture, the singularity is the end of all possible world lines. Nothing continues beyond it. If the interior has structure, then causal relationships might continue in some form. There could be a sense in which events inside still have consequences, even if those consequences are not visible to the outside universe. This opens up philosophical questions about what it means for something to exist if it cannot be observed. Is an interior region that is causally disconnected from the rest of the universe still part of the same physical reality? Different physicists and philosophers answer this in different ways. Some emphasize the importance of observability, others emphasize the consistency of the theoretical framework. This diversity of views reflects the fact that we are still feeling our way through this territory. There is also a connection here to how we think about the beginning of the universe. Many of the same ideas that replace the black hole singularity with a bounce or a finite region are applied to the Big Bang. In some models, the universe did not begin with an infinite point, but with a transition from a previous phase. The same mathematical tools that smooth out the center of a black hole can smooth out the origin of the cosmos. This parallel suggests that the question of imaginary points is not just about black holes. It is about the nature of extremes in physics more generally. It is about whether the universe allows true infinities, or whether it always replaces them with something finite, structured, and, in principle, describable. Notice how the focus has shifted from a single dramatic feature to a broader landscape. The interior of a black hole becomes a place of many possibilities rather than a single fixed outcome. This does not make the mystery go away, it changes its shape. Instead of asking, what is the singularity, the question becomes, what kind of structure replaces it? And how can we tell, even indirectly, what that structure might be? These are questions that connect theory, observation, and imagination. They invite careful calculation, patient measurement, and creative thinking. They also invite a certain kind of calm. The unknown is not a void. It is a space for exploration. Stepping away from imaginary points does not make the black hole less real or less profound. It makes it more physical, more connected to the broader patterns of how science replaces sharp, idealized features with richer, more detailed structures as understanding deepens. Rather than beginning with a dramatic collapse or a swirling edge in space, it can be helpful to start this part of the journey with something almost ordinary, the simple act of counting. 1, 2, 3. Each number steps neatly into the next, creating a sense of continuity. Now, imagine trying to count something that cannot be divided any further, something that comes in indivisible pieces. At that point, the smooth flow of numbers gives way to a different rhythm, a pattern built from discrete steps instead of an unbroken line. This quiet shift from continuous to counted is a useful way to ease into what quantum gravity is trying to do when it refuses to accept infinities. At its heart, quantum gravity is not a single theory, but a family of ideas driven by the same motivation. The goal is to describe gravity using the rules of quantum mechanics, the framework that governs the smallest scales of reality. Gravity, as described by general relativity, works beautifully on large scales. Quantum mechanics works beautifully on small ones. The trouble begins when both scales matter at the same time, such as inside a black hole, or at the earliest moments of the universe. In those extreme environments, the smooth, continuous space-time of general relativity meets the grainy, probabilistic world of quantum theory. The infinities that appear in the equations of classical gravity can be seen as the friction point between these two ways of describing reality. The refusal of infinities, then, is not an arbitrary choice. It is a practical and philosophical stance. If a theory predicts that something becomes infinite, and if that infinity makes it impossible to say what happens next, the theory has lost one of its most valuable qualities, the ability to connect cause and effect. Quantum gravity aims to restore that connection. To see why this matters, it helps to think again about what infinity represents in a physical context. When a calculation says that density becomes infinite, it is claiming that a finite amount of matter is compressed into zero volume. When it says that curvature becomes infinite, it is claiming that space-time bends without limit at a single point. These statements are mathematically precise but physically hard to interpret. Quantum mechanics, by contrast, is built on the idea that there are fundamental limits. You cannot know both the position and momentum of a particle with arbitrary precision. Energy comes in discrete packets. Certain quantities can only take on specific values. This built-in resistance to perfect sharpness and perfect smoothness is one of the reasons quantum ideas are seen as a natural antidote to infinities. One of the simplest ways this shows up is in the concept of a minimum length scale. In many approaches to quantum gravity, there is a smallest meaningful distance, often associated with the Planck length, which is unimaginably small, far beyond anything we can currently measure directly. If such a minimum exists, then the idea of dividing space into smaller and smaller pieces eventually stops making sense. You cannot zoom in forever. There is a point where the notion of smaller loses its meaning. This alone is enough to change how singularities are viewed. If there is a smallest possible volume, then you cannot compress matter into a point with zero size. The collapse inside a black hole would reach a limit, not an infinity. This idea can be implemented in different ways depending on the specific approach to quantum gravity. In loop quantum gravity, space-time is described as a network of discrete loops. These loops form a kind of scaffolding that gives rise to the familiar notion of smooth space at large scales. At very small scales, however, the scaffolding itself becomes visible, and the idea of a perfectly smooth fabric breaks down. In this picture, area and volume are not continuous quantities. They come in discrete units. There is a smallest possible area, a smallest possible volume. This granularity prevents certain quantities from becoming infinite. When applied to black holes, this can lead to models where the collapse of matter slows as it approaches the smallest allowed volume. Instead of forming a singularity, the interior reaches a state of maximum density and then evolves in a different way. Some versions of this idea suggest that the interior might transition into an expanding region, something like a new space-time domain. Others suggest a stable, high-density core. The details vary, but the common theme is the same. The infinity is replaced by a finite structure. String theory takes a different route. It proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. These strings have a finite size, even if that size is incredibly small. Because interactions are spread out over the length of a string, rather than happening at a single point, certain mathematical divergences are softened. The sharp spikes that would lead to infinities in a point-based theory become smoother features. In the context of black holes, this can mean that the center is not a single point, but a region filled with complex stringy structures. The details of this region are still the subject of active research, but the guiding idea is again the same. Replace the infinitely sharp with the finitely extended. There are also approaches that focus less on the building blocks of space-time and more on the role of information. These ideas suggest that what we think of as space and time might emerge from patterns of quantum entanglement, the way different parts of a system are correlated with each other at a deep level. In these models, the geometry of space-time is not fundamental. It is a derived concept, a way of describing how information is organized. From this perspective, a singularity is not a place where something becomes infinite. It is a place where the geometric description stops being the most useful way to talk about what is happening. The underlying structure in terms of information and entanglement continues to exist and evolve. This shift in viewpoint can feel subtle, but it has powerful implications. It suggests that the refusal of infinities is not just about avoiding mathematical problems. It is about choosing the right language to describe reality at different scales. Another way to see this is to think about temperature. In classical physics, temperature is treated as a continuous quantity. You can imagine it increasing or decreasing smoothly. In quantum physics, temperature is related to the average energy of microscopic states, which themselves are discrete. If you try to push temperature to infinity in a quantum system, you run into practical and conceptual problems. There are only so many states available, only so much energy that can be packed into a given system before new physics comes into play. The same logic can be applied to space-time itself. If space-time has a finite number of fundamental states, then certain quantities cannot grow without bound. This idea ties into the concept of black hole entropy. According to the laws of black hole thermodynamics, the entropy of a black hole is proportional to the area of its event horizon, not the volume inside. This suggests that the number of microscopic states associated with a black hole is finite for a given horizon area. If the number of states is finite, then the system cannot support infinite values of physical quantities. There is a built-in cap, even if it is extremely high. This connection between gravity, thermodynamics, and quantum theory is one of the most intriguing aspects of modern physics. It hints that the refusal of infinities might be deeply tied to the way information is stored and processed in the universe. There is also a practical motivation behind all of this. Theories that produce infinities are hard to work with. Calculations become unstable. Predictions become sensitive to tiny changes in initial conditions. This makes it difficult to connect theory with experiment. By developing frameworks that naturally avoid infinities, physicists hope to create theories that are not only conceptually satisfying, but also mathematically robust. This does not mean that the refusal of infinities is guaranteed to be the correct path. It is a working hypothesis, guided by past experience and by the desire for consistency between different areas of physics. History provides some support for this approach. Time and again, when infinities have appeared in physical theories, they have been resolved by the introduction of new concepts. The ultraviolet catastrophe led to quantum mechanics. The collapse of the classical atom led to discrete energy levels. In both cases, the infinities were not features of the world, but of the models used to describe it. This pattern encourages the idea that the singularities predicted by general relativity may also be resolved by a deeper theory. There is, however, an important difference. In the earlier cases, experiments were available to guide the development of the new theories. In the case of quantum gravity, direct experimental access to the relevant scales is extremely limited. This means that much of the work is driven by mathematical consistency, theoretical elegance, and indirect connections to observable phenomena. Physicists look for signs that different approaches converge on similar ideas, such as the importance of horizon area, the role of information, or the appearance of minimum length scales. These convergences are taken as hints that certain features might be pointing in the right direction, even if the full picture is not yet clear. There is also a philosophical aspect to the refusal of infinities. Infinity, as a concept, is deeply rooted in human thought. It appears in mathematics, in philosophy, and in theology. It represents the idea of something beyond all limits. In physics, however, the focus is usually on what can, at least in principle, be related to measurement and observation. An infinite value is not something you can measure. You cannot compare it to anything else. It sits outside the usual framework of empirical science. This does not mean that infinity has no place in the language of physics. It can be a useful way to describe limits and idealizations. But when it appears as a literal prediction about a physical quantity, it raises questions about how that prediction could ever be tested or confirmed. Quantum gravity, in many of its forms, takes the stance that physical quantities should remain finite, even if they become extremely large. This keeps them within the realm of potential observation, at least in principle. There is also a connection here to the idea of predictability. If a theory predicts that a quantity becomes infinite at a certain point, it often cannot say what happens beyond that point. The chain of cause and effect breaks. A theory that avoids infinities can, in principle, continue to make predictions, even in extreme regimes. This continuity is appealing because it preserves the idea that the universe remains governed by consistent rules, even in its most dramatic environments. This does not mean that the rules are simple or easily understood. It means that they do not simply stop. Another interesting angle is the way these ideas affect our understanding of time. In the classical picture of a black hole, all future-directed paths lead to the singularity. Time, in a sense, ends there. If the singularity is replaced by a finite region or a bounce, then time might continue in some form. The structure of that continuation could be very different from what we experience, but the idea of an absolute endpoint becomes less compelling. This opens up speculative possibilities about connections between black holes and cosmology. Some models suggest that the interior of a black hole could give rise to a new expanding region of space-time, with its own timeline. In such a picture, the refusal of infinities is not just a technical fix. It becomes part of a larger story about the creation and evolution of universes. These ideas remain speculative, but they illustrate how a seemingly narrow technical issue, the appearance of infinity in an equation, can lead to far-reaching questions about the nature of reality. There is also a human element to this. The discomfort with infinities reflects a desire for understanding that is complete but not closed. Physicists want theories that are powerful enough to describe the universe in all its complexity, but also grounded enough to remain connected to observation and experience. The refusal of infinities is part of that balance. It is a way of saying that even at the edges of knowledge, we should aim for descriptions that remain meaningful, rather than ones that dissolve into abstract extremes. As you sit with this, it may be helpful to think of quantum gravity not as a single, finished idea, but as a landscape of exploration. Different paths wind through this landscape, each offering a different view of how gravity, space, time, and quantum mechanics might fit together. Some paths focus on geometry, some on information, some on fundamental building blocks. All of them, in one way or another, are responding to the same whisper from the equations, the same signal that something deeper is waiting to be understood. The refusal of infinities in this sense is not a rejection of mystery. It is a commitment to keep the mystery within the realm of the describable, even if the description has to change. Quantum gravity in all its many forms represents a collective attempt to keep the universe within the reach of explanation, even when it reaches its most extreme and challenging expressions. Across the many ways we try to describe the world, there is a quiet pattern that shows up again and again, a tendency for sharp edges to soften, for perfect ideals to blur into something more practical and more physical. Mathematics is very comfortable with extremes. It allows points with no size, lines with no thickness, and values that stretch all the way to infinity. Nature, on the other hand, often seems to hesitate at those same boundaries. When our equations predict something that goes all the way to an absolute limit, the physical world frequently answers back with a subtle modification, a built-in restraint, or a new layer of structure. This difference between what math allows and what nature seems to prefer is not a flaw in either one. It is a reflection of the roles they play. Mathematics is a language of pure possibility. It explores what can be defined logically, even if those definitions have no direct physical counterpart. Physics uses that language to describe a universe that is made of things that can, at least in principle, be measured, compared, and observed. When the two come together smoothly, we get theories that feel both elegant and grounded. When they come apart, we often encounter extremes, infinities, and idealizations that work beautifully on paper, but feel uneasy when we try to connect them to the real world. To ease into this idea, it helps to think about something simple and familiar, like a straight line. In mathematics, A line can be infinitely thin, perfectly straight, and extend forever in both directions. In the physical world, you can draw a line on paper or stretch a string across a room, but it always has some thickness, some texture, some imperfection. The mathematical line is an ideal, the physical line is an approximation. This pattern shows up in many places. A perfect sphere in mathematics has an exactly defined radius and a perfectly smooth surface. A real ball, even one made with great care, has tiny bumps, slight irregularities, and atoms arranged in a structure that is anything but perfectly smooth. These differences are not problems to be solved. They are reminders that our models are tools, not mirrors. They capture essential features of reality, but they do so by simplifying, idealizing, and sometimes pushing things to limits that the physical world never quite reaches. In physics, mathematical extremes often appear when a model is pushed beyond the range where its assumptions hold. When that happens, the equations can produce results that are technically consistent within the math, but physically questionable. One of the clearest examples of this is the idea of a point particle. In many equations, particles are treated as having no size at all. This simplifies calculations and works well in many contexts. But if you take that idea too literally and try to calculate certain properties, like the energy of the electric field around a charged point particle, you can end up with infinite values. This infinity is not usually interpreted as meaning that a real particle has infinite energy. It is taken as a sign that treating the particle as a perfect point is an approximation that breaks down at very small scales. The response to this problem in physics has often been to introduce some form of structure or limit. Instead of a point, you consider an object with a small but finite size. Instead of a perfectly smooth field, you consider fluctuations and quantum effects. The same pattern appears in the study of black holes and singularities. The equations of general relativity treat space-time as perfectly smooth and continuous. They allow it to be curved arbitrarily sharply. When you follow those equations to their logical conclusion inside a black hole, you get a point of infinite curvature. From a mathematical perspective, this is a valid solution. From a physical perspective, it raises questions. Can space-time really be bent without limit? Can matter really be compressed into a point with no size at all? The idea that nature might resist such extremes is not just a philosophical preference. It is supported by patterns seen across many areas of physics. Consider temperature. In classical physics, temperature is a continuous variable. You can imagine it increasing without bound. In quantum physics, temperature is related to the average energy of microscopic states, and those states are discrete. There is a sense in which you cannot keep adding energy in the same way forever. At some point, new degrees of freedom appear, new kinds of behavior become relevant, and the simple picture breaks down. Or think about speed. In everyday experience, you can always go faster by pushing harder. In special relativity, there is a built-in limit, the speed of light. No matter how much energy you add to an object with mass, it never quite reaches that speed. The equations allow you to approach the limit, but they prevent you from crossing it. This is a striking example of nature enforcing a boundary where mathematics might otherwise allow an extreme. The equations of motion are structured in such a way that the extreme value remains out of reach. The same kind of behavior appears in quantum mechanics with the uncertainty principle. It sets a limit on how precisely certain pairs of properties can be known at the same time. You can measure position very accurately, or you can measure momentum very accurately, but not both at once beyond a certain point. This does not mean that the particle itself has an extreme value of uncertainty. It means that the structure of the theory and the structure of reality it describes includes a built-in fuzziness. These examples suggest a broader theme. The physical world often seems to be organized in a way that avoids absolute extremes. It allows things to become very large, very small, very fast, or very dense, but not infinitely so. This theme becomes especially interesting when we look at how physical systems behave near what appear to be critical points. In many areas of science, from physics to chemistry to biology, systems undergo transitions when certain parameters reach particular values. Water turns to ice at a certain temperature. Magnets lose their magnetization above a certain point. Chemical reactions switch behavior when concentrations pass a threshold. Near these transitions, small changes can have large effects. Quantities can grow rapidly. Fluctuations can become large. But even here, there are often limits. The system does not usually jump to an infinite value. It moves into a new phase with different rules. Some physicists think that something similar might be happening inside black holes. As density and curvature increase, the system might reach a kind of critical point where the familiar description of space-time changes. Instead of continuing to grow without bound, the system might enter a new regime with new degrees of freedom and new behavior. This idea fits naturally with approaches to quantum gravity that treats space-time as having a microscopic structure. In those models, there is a smallest possible unit of area or volume. When you reach that scale, the smooth description of space-time gives way to something more like a network or a lattice. At that point, the idea of infinite curvature loses its meaning, because curvature itself is defined in terms of smooth changes over continuous space. If space is not continuous at that scale, then the mathematical notion of curvature has to be replaced by something else. Another way to think about this is in terms of energy. Many physical systems have a maximum energy density they can sustain before their structure changes. For example, if you keep compressing matter, at some point atoms break apart, and you get a plasma of nuclei and electrons. Compress further, and nuclei break apart into quarks. Each stage introduces new physics. In the context of black holes, compressing matter to extreme densities might similarly trigger new kinds of behavior at the level of space-time itself. The fabric of space and time might rearrange, forming new structures rather than continuing to compress smoothly toward a point. There is also a thermodynamic perspective on extremes that adds another layer to this pattern. Thermodynamics deals with quantities like temperature, pressure, and entropy, and it often reveals limits that are not obvious from a purely mechanical point of view. One of the most intriguing connections between black holes and thermodynamics is the relationship between the area of the event horizon and entropy. The fact that the entropy of a black hole is proportional to its surface area, not its volume, suggests that there is a finite number of microscopic states associated with a black hole of a given size. If the number of states is finite, then there is a limit to how much information can be packed into that region. This again points toward a kind of built-in restraint. In this light, the idea of infinite density or infinite information content inside a black hole feels out of place. It would clash with the idea that the horizon area sets a finite bound on entropy. This tension between different parts of our theoretical framework is one of the reasons physicists suspect that the singularity is not a literal feature of reality. It does not fit comfortably with the way other physical principles seem to impose limits. There is also an observational angle to this. In the history of science, whenever a theory has predicted an unbounded extreme, closer examination and better measurements have often revealed a more nuanced reality. Take the example of the Earth. For a long time, it was treated as a perfect sphere in calculations. This worked well for many purposes. As measurements became more precise, it became clear that the Earth is slightly flattened at the poles and bulges at the equator. The ideal sphere was replaced by a more detailed model. Or consider the behavior of gases. The ideal gas law describes a simple relationship between pressure, volume, and temperature. It works well under many conditions. At very high pressures or very low temperatures, real gases deviate from this ideal behavior. The model breaks down, and more complex descriptions are needed. These examples show a common pattern. Simple models often predict extremes when pushed too far. Real systems introduce new effects that soften or alter those predictions. This does not mean the simple models are wrong. It means they have a domain of validity. The same reasoning can be applied to general relativity. It is an extraordinarily successful model of gravity at large scales and moderate energies. The appearance of singularities and infinities suggests that its domain of validity may not extend all the way to the smallest possible scales and highest possible energies. This perspective frames the problem of singularities not as a failure of understanding, but as a natural point of transition between different levels of description. There is also a deeper philosophical idea at work here, one that goes back to the way we think about measurement. To say that something has a certain value, we need a way to measure it. Measurement always involves some finite resolution. There is always a smallest increment we can distinguish. If the universe itself has a smallest meaningful scale, then physical quantities cannot vary smoothly all the way down to zero size or up to infinite density. They must change in steps, even if those steps are extremely small. This idea aligns with the way quantum mechanics treats many aspects of reality. Energy levels in atoms come in discrete values. Angular momentum is quantized. Even light comes in packets. Extending this logic to space-time suggests that area and volume might also be quantized. If so, the idea of a point with zero volume becomes as unphysical as the idea of an atom with zero energy. There is also an aesthetic dimension to this. Many physicists are drawn to the idea that the universe has a kind of internal consistency, a set of patterns that repeat across different scales and contexts. The appearance of limits, thresholds, and transitions in so many areas of physics suggests that this might be part of a deeper pattern. Instead of allowing quantities to run off to infinity, the universe often introduces new structures and new rules at critical points. This pattern can be seen in phase transitions, in symmetry breaking, and in the emergence of new particles and forces at high energies. In this context, the center of a black hole might be another such critical point, not an end point, but a place where the familiar description gives way to something new. This does not mean that nature is deliberately avoiding infinity in some purposeful sense. It means that the structures we observe and the theories that describe them tend to be organized around finite relational quantities rather than absolute extremes. There is also a practical reason for this in terms of stability. Systems that push variables to extremes often become unstable. Introducing limits can create stability. For example, the speed of light limit ensures that cause and effect remain well ordered in space-time. The uncertainty principle prevents particles from collapsing into arbitrarily small regions of space. These limits are not arbitrary. They help maintain the internal consistency of the physical world. Applying this idea to black holes suggests that some kind of limit might also operate there, preventing the formation of a true singularity. This line of thought is still being explored, and there is no consensus on the details. But the recurring pattern of nature avoiding or reshaping mathematical extremes gives physicists reason to take the idea seriously. It also connects back to the broader theme of this journey, that the singularity may be more about the limits of our descriptions than about the presence of a literal physical point of infinity. The black hole itself is a real, measurable object. Its mass, its spin, its horizon, and its influence on its surroundings can be observed and tested. The singularity sits beyond that, in a region where our current models push into abstraction. Nature's apparent reluctance to allow true mathematical extremes suggests that something else might be waiting there, something finite, structured, and, in principle, describable, even if we do not yet have the tools to describe it. As you let this idea settle, it can be helpful to think of physics as a layered story. Each layer provides a way of talking about the world that works within a certain range. When you move beyond that range, the language changes. Newton's laws work well at everyday speeds and scales. Relativity takes over when speeds and gravitational fields become large. Quantum mechanics becomes important at very small scales. Quantum gravity aims to describe the places where all of these layers overlap. The appearance of infinities often marks the boundary between one layer and the next. This perspective turns the idea of an extreme from something final into something transitional. It is not the end of the story. It is the place where the story changes its vocabulary. there is a certain calm in that view. It suggests that the universe is not built around unreachable absolutes, but around a series of interconnected descriptions, each one giving way to the next as conditions change. The black hole, in this sense, becomes a kind of bridge between layers of understanding. It is a place where the smooth geometry of space-time meets the discrete, uncertain world of quantum mechanics. And at that meeting point, the sharp, idealized features of mathematics may soften into the textured, finite structures of physical reality. Nature often seems to prefer the finite over the infinite, the structured over the absolute, and the relational over the extreme. The mathematical language we use to describe the universe can stretch to infinity. The universe itself, in many subtle ways, appears to draw its lines a little closer, offering not endless escalation, but a sequence of transitions, each one opening into a new and different kind of understanding. Seen from a certain angle, it can be tempting to think of a black hole as a kind of mistake in the universe, a glitch where the normal rules broke down and left behind something dark and unreachable. The language we use does not always help. Words like singularity, collapse, and infinite density make it sound as if reality itself stumbled and never quite recovered. But there is another way to look at these objects, one that feels steadier and in many ways more grounded. Instead of treating black holes as cosmic errors, you can treat them as natural outcomes, ordinary in their own extreme way, shaped by the same rules that guide stars, planets, and galaxies. To ease into that perspective, it helps to think about how a black hole actually comes into being. It does not appear out of nowhere. It is not dropped into the universe like a foreign object. It grows out of a process that begins with something familiar, a star. Stars form from clouds of gas and dust that slowly collapse under their own gravity. As the material falls inward, it heats up. When the core becomes hot and dense enough, nuclear reactions begin and the star starts to shine. For millions or billions of years, there is a balance between two opposing tendencies. Gravity tries to pull everything inward. The energy released by nuclear fusion pushes outward. The star exists in a kind of steady tension between these forces. Eventually, for some stars, the fuel runs low. The outward push weakens. Gravity gains the upper hand. The star begins to contract. What happens next depends on how much mass the star has. Smaller stars settle into dense remnants like white dwarfs. Larger ones can collapse into neutron stars. The most massive ones continue collapsing until even the pressure of tightly packed neutrons cannot stop the inward fall. At that point, an event horizon forms and a black hole is born. This sequence is not an accident. It is a consequence of the same physical laws that govern the star's life from the beginning. The black hole is not a failure of the star. It is one of the possible endings written into the rules of gravity and nuclear physics. From this viewpoint, a black hole is less like an error message and more like a chapter in a longer story. It is what happens when a certain set of conditions is met, just as a supernova is what happens when a massive star reaches the end of its ability to support itself. There is a similar story on a larger scale. In the centres of galaxies, including our own Milky Way, sit supermassive black holes with masses millions or billions of times greater than that of the Sun. These giants did not form from the collapse of a single star. They grew over time through the merging of smaller black holes and the slow accumulation of gas and stars from their surroundings. This process is tied to the evolution of the galaxies themselves. Observations show a close relationship between the mass of a galaxy's central black hole and the properties of the galaxy's bulge of stars. This suggests that the growth of the black hole and the growth of the galaxy are connected. In this context, the black hole is not an isolated oddity. It is part of a larger system. It influences how gas moves, how stars form, and how energy is distributed on galactic scales. When a supermassive black hole is actively pulling in material, it can release enormous amounts of energy into its surroundings. Jets of high-energy particles can shoot out from the regions near the horizon, extending for thousands of light years. Radiation from the hot gas in the accretion disk can heat and push away surrounding material. These processes can slow down or even halt star formation in parts of the galaxy. In this way, the black hole acts as a kind of regulator, helping shape the long-term evolution of the galaxy. This role is difficult to square with the idea of a cosmic error. Errors do not usually play such integrated, constructive parts in larger systems. Black holes, by contrast, appear to be woven into the fabric of cosmic history. Another way to see this is to look at how common they are. Astronomers estimate that there may be millions of stellar mass black holes in our galaxy alone. They are not rare anomalies. They are a natural outcome of the life cycle of massive stars. Most of these black holes are quiet. They do not have glowing disks or dramatic jets. They simply exist, moving through the galaxy, occasionally interacting with other objects, but often going unnoticed. This quiet abundance gives them a kind of normalcy. They are not special cases. They are one of the many kinds of objects that populate the universe. There is also a mathematical sense in which black holes are not errors. In general relativity, they arise as well-defined solutions to the equations. The Schwarzschild solution, which describes a simple, non-rotating black hole, is not a pathological case. It is a clean, elegant expression of how space-time can be shaped by mass. More complex solutions describe rotating black holes, charged black holes, and black holes in expanding universes. These solutions fit naturally into the framework of the theory. They are not tacked on as exceptions, they are part of the structure. This does not mean that every aspect of these solutions is fully understood. The singularity at the center remains a place where the theory likely breaks down. But the existence of the black hole itself, the horizon, the way it influences its surroundings, and the way it evolves over time are all described within a consistent, tested framework. This distinction is important. It separates the object from the limits of our description of its interior. The black hole is not the problem. The singularity is where the problem appears. Another perspective that helps recast black holes as objects rather than errors comes from thermodynamics. Black holes follow laws that closely resemble the laws of thermodynamics. They have a temperature, related to the surface gravity at the horizon. They have an entropy, related to the area of the horizon. These properties are not arbitrary. They fit into a broader pattern of how physical systems behave. The fact that black holes can be assigned a temperature and an entropy suggests that they are not outside the domain of physical law. They are part of it. The entropy of a black hole is especially intriguing. It is enormous, far greater than the entropy of an ordinary star of the same mass. This reflects the idea that a black hole can exist in a vast number of microscopic states, even if we cannot directly observe them. This way of thinking turns the black hole into a kind of thermodynamic system, one that exchanges energy and information with its surroundings in subtle ways. The possibility that black holes slowly lose mass through Hawking radiation adds another layer to this picture. Over extremely long timescales, a black hole can evaporate, returning its energy to the universe in the form of radiation. This process is unimaginably slow for large black holes, but it suggests that even these extreme objects are not permanent. They are part of the ongoing flow of energy and matter through the cosmos. Seen this way, a black hole is not a dead end. It is a stage in a cycle, a way that mass and energy can be stored for long periods before being released again. There is also a conceptual shift that happens when you think of black holes as objects rather than errors. An error suggests something that should not be there, something that violates the intended design. An object suggests something that has properties, behaviors, and relationships. When physicists study black holes, they do not just ask what they are. They ask how they interact. How do they merge? How do they accrete matter? How do they influence their environments? These questions treat black holes as participants in physical processes, not as exceptions to them. The mergers of black holes, detected through gravitational waves, are a striking example. When two black holes spiral toward each other and combine, they produce a characteristic pattern of space-time ripples that can be measured here on Earth. The shape of those ripples tells us about the masses and spins of the black holes involved. It also tests the predictions of general relativity and strong gravitational fields. The fact that these predictions have been confirmed so far suggests that black holes behave in a consistent, rule-governed way, even in these extreme events. This consistency reinforces the idea that black holes are not places where physics stops working. They are places where physics is pushed to its limits, but still functions in many respects. There is also an aesthetic dimension to this. Many physicists are drawn to the elegance of the black hole solutions in general relativity. The way a complex dynamic process like gravitational collapse can lead to a simple, well-defined object is seen as a kind of beauty. The idea that a black hole can be fully described by just a few numbers, despite the complexity of what falls into it, suggests a deep simplicity underlying the apparent chaos. This simplicity does not erase the mystery. It frames it. It tells us that there is a structure there, even if we do not yet understand all of it. Another way to move away from the idea of cosmic error is to consider how black holes fit into the broader pattern of extremes in nature. The universe is full of objects and phenomena that operate at the edges of what we consider normal. Neutron stars have densities that compress atomic nuclei together. Quasars shine with the light of trillions of stars. Gamma-ray bursts release more energy in seconds than the sun will in its entire lifetime. These are not errors. They're expressions of the same physical laws operating under different conditions. Black holes belong in this family. They are not violations of the rules. They are what happens when the rules are applied in a regime of extreme mass and compactness. This perspective can make them feel less alien. They become part of a continuum rather than an exception. There is also a philosophical aspect to this shift. Treating something as an error often implies that there is a correct state of the universe, and that this thing deviates from it. Treating something as an object implies that it belongs, that it has a place in the overall pattern. In science, the latter view tends to be more productive. Instead of asking why something is wrong, you ask how it works. When physicists approach black holes with that mindset, they uncover connections to other areas of physics, from thermodynamics to quantum information. These connections suggest that black holes are not isolated curiosities, but central players in the deeper structure of physical law. For example, the study of black hole entropy has influenced ideas about the nature of information in the universe. The holographic principle, which emerged from thinking about black holes, has found applications in areas as diverse as condensed matter, physics, and quantum computing. In this way, black holes have become sources of insight, not just objects of mystery. Another subtle point is how the idea of an error can shape expectations. If you expect a black hole to be a place where physics breaks down completely, you might overlook the many ways in which it behaves predictably and consistently. Recognizing the black hole as an object encourages a more balanced view. You can acknowledge the limits of current theories while still appreciating the areas where those theories work remarkably well. This balance is reflected in the way physicists talk about singularities. They do not usually say that the black hole itself is a singularity. They say that the theory predicts a singularity at the center. This phrasing keeps the focus on the model rather than the object. It leaves open the possibility that the true interior is something different. In that sense, calling black holes cosmic errors might be more about our discomfort with the singularity than about the black hole itself. There is also a connection here to how we think about the beginning of the universe. The Big Bang is often described as a singularity, a point where our equations break down. But the universe itself is not usually treated as an error. It is treated as a fact, a given. The breakdown of the equations at the beginning of time is seen as a challenge for theory, not as a flaw in reality. The same logic can be applied to black holes. The breakdown of the equations at the center is a challenge for our understanding, not a sign that the object itself should not exist. This parallel reinforces the idea that singularities are markers of the limits of our descriptions, not markers of mistakes in the universe. There is also an emotional element to how we relate to black holes. The idea of something that swallows light and hides its interior can evoke a sense of unease. Reframing black holes as objects with a place in the cosmic order can soften that feeling. They become less like voids and more like landmarks, less like threats and more like features. This does not remove the sense of awe, it changes its tone. Instead of being awed by something that seems to break the rules, you can be awed by something that follows the rules to an extreme conclusion. That conclusion leads to a region we do not yet fully understand, but it does so in a way that is consistent with the broader patterns of the universe. The black hole stands not as a mistake, but as a natural outcome, a participant in the ongoing story of stars, galaxies, and the evolution of the universe. It is a place where the rules we know reach their limits, but also a place where those limits invite new ideas. Instead of beginning with a collapse or a boundary, it can be useful to start this part of the story with a pause, the kind you take when you reach the end of a familiar path and notice that the ground ahead looks different. There is no signpost telling you exactly where to go next, only a sense that the old map no longer quite fits the landscape. This is the position physicists find themselves in when they ask what, if anything, replaces the singularity inside a black hole. The singularity, as it appears in the equations of general relativity, is a clear and simple feature on paper. It is the place where certain quantities become infinite and the usual rules stop giving meaningful answers. For a long time, it has served as a kind of placeholder, a marker for the point where our current description reaches its limit. But a placeholder invites replacement. It suggests that something else, something more detailed or more physically grounded, might eventually take its place. To explore what that something else might be, it helps to think about what the singularity is meant to represent in the first place. In the standard picture, it is the endpoint of collapse, the ultimate concentration of mass and energy into an infinitely small region. It is where space-time curvature becomes unbounded and the familiar structure of cause and effect seems to unravel. If you step back from the mathematical language and ask what this means in physical terms, you quickly run into trouble. Infinite density and infinite curvature are not quantities you can measure or observe. They are not states you can compare to anything else in the universe. They are, in a sense, beyond the usual vocabulary of physics. This is why many physicists suspect that the singularity is not a literal feature of reality, but a sign that the theory being used has run out of applicability. From that starting point, a wide range of ideas opens up, each offering a different answer to the question of what might replace the singularity. One of the simplest possibilities is that the singularity is replaced by a region of extremely high but finite density and curvature. Instead of a point, there is a small core. Instead of an infinite spike, there is a steep but bounded peak. This idea fits naturally with the notion that there is a smallest meaningful length scale in nature. If space cannot be divided indefinitely, then there is a limit to how small a region can become. Matter collapsing inside a black hole would reach that limit and then have to respond in some other way. In this picture, the interior of a black hole would contain a compact dense object, sometimes referred to in the literature as a Planck star or something similar. The name reflects the idea that its size and properties would be governed by Planck scale physics, where quantum effects become dominant. Such an object would not be a star in the usual sense. It would not shine or burn. It would be more like a core of space-time and matter in an unfamiliar phase, held in a state of extreme compression by gravity and by the rules of quantum mechanics. The details of how such a core would behave are still speculative. Some models suggest it could be long-lived, persisting for times far longer than the age of the universe as we experience it. Others suggest it could eventually transform, releasing energy or information in some subtle way. Another class of ideas involves the concept of a bounce. Instead of collapse ending in a static core, the inward fall might reverse direction at very small scales. The collapsing matter and space-time could transition into an expanding phase. In some models, this expansion does not lead back into the same universe. It leads into a new region of space-time, sometimes described as a baby universe. From the outside, all you see is a black hole. From the inside, the bounce could look like a big bang. This idea creates a kind of symmetry between black holes and the origins of universes. The singularity at the center of a black hole becomes analogous to the singularity at the beginning of the cosmos, both replaced by transitions between phases rather than absolute endpoints. This picture is imaginative, but it is grounded in specific mathematical frameworks. In certain approaches to quantum gravity, the equations naturally lead to bounce-like behavior when densities and curvatures reach extreme values. There are also models that focus on the role of information, rather than on the structure of matter and space-time. These approaches suggest that the singularity is replaced by a different way of organizing information. In this view, what falls into a black hole is not destroyed or compressed into a point. Instead, it becomes encoded in subtle correlations, perhaps spread across the horizon or woven into the quantum state of the black hole as a whole. The interior, from this perspective, is not a place in the usual geometric sense. It is a pattern of relationships between quantum degrees of freedom. The singularity is replaced by a highly entangled state, one that does not lend itself to a simple spatial description. This idea is connected to the holographic principle, which suggests that the information content of a volume of space can be described by data on its boundary. Applied to black holes, this principle implies that everything that happens inside might be fully represented by what is happening on the horizon. If that is the case, then the replacement for the singularity is not a structure at the center, but a structure at the boundary. The horizon becomes the key player, the place where the essential physics is encoded. Another possibility is that the interior geometry itself is more complex than the simple picture of a smooth collapse to a point. Some solutions to Einstein's equations, especially when extended or modified, allow for more elaborate internal structures. These can include regions where space-time connects to itself in unusual ways, forming tunnels or bridges. In popular language, these are sometimes called wormholes. In certain theoretical models, the interior of a black hole might contain such a structure, linking it to another region of space-time. The singularity, in this case, is replaced by a kind of passage. These ideas are highly speculative, and there is no direct evidence that such structures exist. But they illustrate how the question of replacement can lead to very different kinds of answers depending on which aspects of physics you emphasize. There are also more conservative approaches that focus on modifying the equations of general relativity itself. Instead of introducing a full theory of quantum gravity, these approaches add extra terms or corrections to the existing equations. These modifications can change the behavior of space-time at very high curvatures, preventing quantities from becoming infinite. The result is often a regular non-singular solution, where the center of the black hole is a smooth region rather than a point of divergence. These models are attractive because they stay close to a well-tested framework while addressing one of its most troubling features. The challenge is to find modifications that are both mathematically consistent and physically motivated, and that do not conflict with observations in regimes where general relativity works well. There is also an approach that shifts the question in a different direction. Instead of asking what replaces the singularity, it asks whether the singularity is something that exists at all, even in principle. This line of thought emphasizes the role of observers and measurements. The interior of a black hole is causally disconnected from the outside universe. No signal from the center can reach an external observer. From this perspective, the singularity is not something that can ever be observed or tested. It is a feature of a theoretical extension of the equations, not of empirical reality. Some physicists argue that in such a case, the question of what replaces the singularity might be less meaningful than it seems. What matters physically is what can be observed, and that is limited to the horizon and the region outside it. This does not mean that the interior is unimportant. It means that our access to it is indirect. Any model of the interior must ultimately be judged by its consistency with what we can observe from the outside. This observational constraint acts as a kind of filter on speculative ideas. Models that predict dramatic effects at the horizon or in the radiation emitted by the black hole can, in principle, be tested. Models that confine all their novelty deep inside may be harder to evaluate. This interplay between theory and observation is an important part of the story. It keeps the question of replacement grounded, even as it invites imaginative possibilities. Another angle on this question comes from the study of black hole evaporation. According to Hawking's calculations, black holes are not completely black. They emit radiation and lose mass over time. If a black hole evaporates completely, what happens to the information that fell into it? This is known as the information problem. If there is a singularity that destroys information, that seems to conflict with the principles of quantum mechanics, which suggest that information should be conserved. Many proposed replacements for the singularity are motivated, at least in part, by the desire to resolve this tension. If the interior has a structure that preserves information in some form, even if it is hidden or transformed, then the conflict can be eased. For example, in models where the interior leads to a baby universe, the information might be carried into that new region. From the perspective of the original universe, it appears lost. From a broader perspective, it is still part of the overall physical system. In models where information is encoded on the horizon, the interior becomes less relevant to the question of conservation. The singularity is replaced by a different kind of accounting system, one that operates at the boundary rather than at the center. These ideas show how the question of what replaces the singularity is tied to deeper issues about the nature of information, measurement, and the scope of physical law. There is also a practical side to this exploration. Many of these models make subtle predictions about how black holes should behave, especially in dynamic situations like mergers or during the late stages of evaporation. As observational technology improves, physicists hope to look for signatures of these effects. Tiny deviations in the pattern of gravitational waves, unexpected features in the radiation from black holes, or anomalies in the motion of matter near the horizon could in principle provide clues. So far, the observations are consistent with the predictions of general relativity. This does not rule out more complex interiors. It simply means that any replacement for the singularity must be subtle enough not to disrupt the behavior of the black hole in the regimes we can observe. This constraint is both limiting and guiding. It narrows the range of viable ideas while also focusing attention on those that can be connected, even indirectly, to empirical data. Another theme that runs through many of these ideas is the role of scale. What happens at the smallest possible scales can have implications for the largest possible structures. If the interior of a black hole is connected in some way to the origin of a universe, then the physics of the very small and the physics of the very large are linked. This kind of connection is appealing because it suggests a kind of unity in the laws of nature. The same principles that govern the collapse of a star could, in some form, govern the birth of a cosmos. Whether this is more than a poetic symmetry remains to be seen, but it illustrates how the question of replacement opens up a wide landscape of ideas, spanning from the technical details of quantum geometry to the grand structure of the multiverse. There is also a more modest possibility that the singularity is replaced by something we have not yet imagined, something that does not fit neatly into our current categories of matter, energy, space, or information. History offers many examples of such surprises. Before the discovery of atoms, matter was thought to be continuous. Before the discovery of quantum mechanics, energy was thought to be infinitely divisible. In both cases, new concepts reshaped the way reality was understood. The interior of a black hole may be another place where a new concept is needed. This openness is part of what makes the question compelling. It is not just a technical puzzle. It is an invitation to rethink some of the most basic ideas we use to describe the world. What is space if it can be replaced or transformed at extreme densities? What is time if it can continue through a bounce or be encoded in correlations rather than in a sequence of moments? What is information if it can be stored on a surface or carried into a new region of space-time? These questions extend beyond black holes. They touch on the foundations of physics as a whole. As you let this exploration settle, notice how the focus has shifted from a single point to a range of possibilities. The singularity, once imagined as a hard endpoint, becomes a doorway to many different conceptual paths. This does not make the problem easier, it makes it richer. The lack of a single, agreed-upon replacement reflects the current state of the field. Physicists are still mapping this territory. Different approaches highlight different aspects of the problem, and it is not yet clear which, if any, will lead to a complete and testable theory. There is also a sense in which this uncertainty is appropriate. The interior of a black hole is one of the most extreme environments in the universe. It would be surprising if it yielded easily to our first attempts at description. This perspective encourages patience. Instead of expecting a simple answer, it invites a gradual refinement of ideas, guided by both mathematical consistency and observational clues. The question of what replaces the singularity, if anything does, is less about finding a single object or structure, and more about developing a framework that can describe a new regime of reality. In that sense, the singularity is not just a feature of black holes, it is a marker for a frontier in physics. After travelling through ideas that stretch the imagination and press against the limits of what can be known, there is value in slowing down and letting the edges blur a little. Not everything needs to be resolved sharply. Some questions are better approached the way you might approach a distant horizon, aware of its presence, oriented by it, but not rushing toward it. Black holes, singularities, quantum gravity, and the refusal of infinity all bring us to that kind of edge, a place where certainty relaxes and curiosity becomes gentler. It can be helpful to notice how different this feels from the way black holes are often presented. Popular descriptions tend to emphasize violence, destruction, and finality. Stars are torn apart, light is trapped, space collapses inward. Those images are not wrong, but they are incomplete. They focus on motion and drama, on what happens when things fall in, rather than on what remains stable, structured, and quietly persistent. When you step back, black holes begin to look less like cosmic disasters and more like long-lived features of the universe, settled into their environments, interacting slowly and predictably with the space around them. They orbit, they merge, they grow, they fade. On the largest timescales, they participate in a kind of cosmic rhythm that is far slower and calmer than human intuition usually allows. This perspective matters when thinking about mystery itself. Mystery does not always mean chaos. Sometimes it simply means that our current descriptions have softened at the edges, becoming less precise but not meaningless. The singularity is one such softened edge. Earlier, it appeared as a hard limit, a place where equations stopped and infinities appeared. But as the exploration unfolded, that sharpness began to dissolve. The singularity became less like a physical object and more like a sign that a particular way of speaking had reached its boundary. What replaces it, if anything, remains open. But what is already clear is that the presence of mystery does not imply the absence of structure. Black holes are among the most carefully studied objects in modern astrophysics. Their masses can be measured, their spins can be inferred, their mergers can be heard through gravitational waves, their shadows can be imaged against glowing disks of hot gas. Even their temperatures and entropies can be calculated. This combination of precision and uncertainty is unusual. It creates a space where confidence and humility coexist. There is something quietly reassuring about that balance. It suggests that the universe is not withholding its secrets out of indifference or hostility. It suggests that understanding unfolds in layers, with each layer revealing new questions that are not failures, but invitations. The edge of a black hole is a literal boundary in space-time, but it is also a metaphorical one. It marks the transition between what can be observed and what must be inferred, It separates direct measurement from theoretical extension. Standing at that edge, physicists are not confronted with nothingness. They are confronted with choice. How should the next description be built? What assumptions should be kept, and which should be set aside? That process takes time. It requires patience, testing, revision, and often long periods where multiple ideas coexist without a clear winner. In that sense, black holes teach a broader lesson about knowledge itself. They remind us that understanding is not a straight line from ignorance to certainty. It is a gradual reshaping of questions, where answers often change the form of what is being asked. This is especially true when dealing with extremes. The universe does not seem to favour absolute limits in the way mathematics does. Instead, it favours transitions. When one description reaches its breaking point, another tends to emerge. This pattern can be seen throughout physics. Classical mechanics gave way to relativity and quantum mechanics, not because it was wrong, but because it was incomplete. Thermodynamics did not replace mechanics, but reframed it. Field theories did not erase particles, but contextualized them. Black holes sit at the intersection of several such transitions. Gravity, quantum mechanics, thermodynamics, and information theory all meet there, each contributing part of the picture, none yet offering the whole. That incomplete convergence is not a failure. It is a sign that the question being asked is deep enough to require more than one perspective. When you let that settle, the idea of resting at the edge begins to feel appropriate. There is no urgency to resolve everything immediately. Some problems take decades or centuries to unfold. Some insights only become visible when technology, mathematics, and intuition align. In the meantime, there is value in recognizing what is already known and how far it reaches. Black holes are real. Their existence is no longer speculative. Their influence is woven into the structure of galaxies. Their mergers shake space-time itself. Their horizons obey precise laws. They are not imaginary constructs or mathematical curiosities. The singularity, by contrast, remains a feature of description rather than observation. It is where current language becomes strained. That distinction is subtle, but important. It means that mystery is localized. It is not spread everywhere. Most of the black hole is well described. Only the deepest interior remains uncertain. That localization allows curiosity to soften rather than harden. Instead of facing an impenetrable wall, you're standing before a doorway that has not yet been opened. There is also something calming in realizing that nothing about this uncertainty threatens the coherence of the universe as a whole. Stars still form, galaxies still evolve, physical laws still hold where they have been tested. The presence of unanswered questions at the extremes does not destabilize the everyday workings of reality. On the contrary, those questions often enrich the rest of physics. Ideas developed to understand black holes have influenced fields far removed from astrophysics. Concepts like entropy, horizons, and information flow now appear in condensed matter physics, quantum computing, and even theories of space-time emergence. This cross-pollination suggests that black holes are not isolated puzzles. They are connective points, places where different strands of understanding meet and inform one another. From that vantage point, the edge becomes a place of quiet productivity rather than tension. There is also a temporal dimension to this calm. Black holes operate on timescales that are vast beyond human experience. A stellar mass black hole can persist for times far longer than the current age of the universe. A supermassive black hole will outlast most of the structures around it. Even Hawking radiation, which slowly erodes black holes over immense durations, acts on timescales so long that they border on the abstract. This slowness invites a different kind of thinking. It shifts attention away from dramatic moments and toward enduring processes. The black hole is not constantly consuming or collapsing. Most of the time, it is simply there. That sense of presence rather than action aligns naturally with rest. When thinking about sleep-oriented science, this matters. The goal is not to provoke alertness or tension. It is to offer ideas that can be held lightly, without the need for immediate resolution. Mystery, when framed gently, can be soothing. It allows the mind to wander without pressure. The idea that some questions remain open does not have to feel unsettling. It can feel spacious. It creates room for imagination without demanding conclusion. At the edge of a black hole, nothing is being asked of you. There is no decision to make, no answer to produce. There is only awareness of how much has been learned and how much remains to be explored. That awareness can settle into something like acceptance. Acceptance does not mean resignation. It means recognizing that understanding unfolds at its own pace. In science, this pace is often slower than personal curiosity would prefer, but it is also steady. Each generation builds on the last. Each refinement adds clarity without erasing what came before. Black holes themselves embody this layered stability. Their external behavior can be described cleanly, even while their interiors remain mysterious. That coexistence shows that partial understanding is still meaningful. You do not need to know everything about an object to know something true about it. That lesson extends beyond physics. It applies to many areas of thought and experience. There are aspects of life, of consciousness, of time itself that remain unresolved. That does not make them chaotic or threatening. It makes them deep. Depth is not the same as danger. The idea that the universe may never allow true mathematical extremes, that infinities are signals rather than realities, fits naturally into this calming view. It suggests that nature prefers continuity over rupture, transitions over endpoints. Even where models break down, reality may remain structured, just structured differently than expected. That perspective removes some of the fear often associated with cosmic extremes. The black hole is not a tier in reality. It is a region where reality follows rules that are still being uncovered. Those rules may be unfamiliar, but unfamiliar does not mean hostile. As the exploration comes to rest here, it is worth noticing how the tone has shifted from questioning to quiet observation. The earlier sections pressed into limits, examined failures of description, and traced the edges of knowledge. Now, there is less urgency. The questions remain, but they no longer demand immediate answers. Instead, they can be held in the background, like distant stars whose light continues to arrive even when you stop actively looking for them. The universe does not require constant interpretation. It continues whether or not it is fully understood. That realization can be deeply relaxing. There is no need to resolve the singularity tonight. No need to decide which theory will succeed or which picture of the interior is correct. Those answers will emerge gradually through work that continues across decades. For now, it is enough to recognize that the black hole, so often framed as an ending, is better understood as a boundary between descriptions. Boundaries are not failures, they are transitions. Standing at the edge, you can allow the mind to loosen its grip on precision and let the larger pattern take over. The pattern is one of continuity, restraint, and layered understanding. Nothing explodes, nothing vanishes. The universe simply continues, quietly complex, patiently unfolding. In that continuation, mystery does not loom. It settles, and as it settles, it becomes less something to confront and more something to rest beside, like the distant hum of a process too large and too slow to disturb the present moment. You do not need to cross the edge to appreciate it. You only need to acknowledge that it is there and that it does not threaten the coherence of what surrounds it. The black hole remains, the questions remain, the universe remains. And with that steady presence, there is space to relax, to let the mind drift, and to allow curiosity to soften into calm. Not because everything has been answered, but because nothing urgent is being asked. At the edge, where explanation fades into possibility, there is room for rest,